Welcome to the mechanics of rest. Set down for a little while the small directions the day has asked you to hold, the choices that needed answering, the paths that had to be followed, the thoughts that kept pointing toward one more task. None of them need arranging now. The mind can loosen its grip on where everything belongs, and the body can be allowed to rest without preparing for the next decision. If the mechanics of rest has become a calm place for slow science and sleep, subscribing helps new episodes arrive each week. A quiet like is also appreciated, a small signal that this patient kind of work is welcome. What actually exists above and below our solar system begins with a simple difficulty. Before anything can be called above or below, some plane must first be chosen. From that first act of orientation, the familiar flatness of the planets opens into tilted orbits, distant icy paths, soft solar boundaries, and the larger galactic motion carrying everything along. For now, the first surface is only a reference, and the science can enter there. Chapter 1: The plane that is not a floor. No direction in space carries the meaning that a body on Earth gives to above or below. A falling stone has a downward path because Earth is there beneath it, drawing it toward the ground, and a standing person inherits that direction without needing to name it. The solar system has no such floor. It has motion, gravity, light, distance, and habit, but not an upper side assigned by nature. Before any object can be described as above or below the solar system, a plane has to be chosen, and that choice is the beginning of the map rather than the end of the question. The plane most often chosen is the ecliptic, the broad surface traced by Earth as it moves around the Sun. It is not visible. No dust sheet marks it in ordinary space. No material membrane divides the solar system into two halves, and no spacecraft crossing it passes through a surface. It is a mathematical agreement built from a real orbit, useful because Earth's motion gives observers a steady reference from which the positions of planets, comets, asteroids, and distant bodies can be measured. In that sense, the ecliptic is one of the quiet instruments of astronomy, a surface that exists because motion can be described with enough care. Long before the ecliptic became a coordinate plane in modern astronomy, it appeared as the path of the Sun across the sky. Ancient observers saw the Sun move against the background of stars over the course of the year, passing through the same broad band where the Moon and planets also wandered. This band was not understood at first as the projection of Earth's orbit, because Earth itself was not yet placed in motion. The sky seemed to turn around the observer, and the wandering lights seemed to move along their own appointed roads. The old description preserved the appearance, even when the cause remained hidden. Copernicus altered the geometry by moving Earth away from the center. In the system he published in the 16th century, Earth became one planet among others, circling the Sun rather than resting beneath the heavens. That change did not immediately make the solar system simple. Circular motions and nested constructions still remained in the model, because older habits in astronomy did not fall away all at once. Yet the essential displacement had occurred. Earth's yearly path around the Sun could become the basis for understanding the apparent yearly path of the Sun through the stars, and the ecliptic could gradually change from a sky path into the shadow of an orbit. Kepler narrowed the old symmetry further. Working from Tycho Brahe's careful observations of Mars, he found that the planet would not obey a perfect circle. The discrepancy was small enough to tempt a less patient mathematician into concealment, but Kepler kept the mismatch alive until the ellipse became unavoidable. Mars moved around the Sun along an oval path, with the Sun at one focus, and the other planets could be understood through the same family of curves. What had looked like a celestial preference for perfect circles gave way to a more exact order, quieter and less ornamental, but closer to the motions themselves. The miniature of Kepler with Mars is useful because it shows how astronomy often changes. A planet does not need to behave dramatically in order to revise a world picture. It only needs to remain slightly misplaced after every calculation that should have accounted for it. Tycho's measurements, gathered before the telescope became an astronomical instrument, were accurate enough to leave Kepler with a stubborn remainder. From that remainder came the ellipse, and from the ellipse came a solar system whose plane was no longer the polished circle of inherited philosophy, but a working geometry of bodies moving under rules. Newton gave those rules their deeper continuity. A planet did not need a separate celestial nature to keep it moving, and a falling body on Earth did not belong to a different physics from the Moon. Gravitation made one language for both, so that orbital motion could be understood as falling that continually missed the central body. Under that description, the ecliptic was not a sacred band or a decorative line in the heavens. It was the approximate common sheet in which several large bodies happened to move, each held by the sun's gravity, each carrying its own speed and distance into a path that remained close to the paths of the others. Most of the major planets keep near that shared sheet. Earth defines it by convention, while Venus, Mars, Jupiter, Saturn, Uranus, and Neptune remain only modestly inclined to it. Mercury is the inner exception among the classical planets, with an orbit tilted about 7 degrees relative to the ecliptic. Pluto, no longer counted among the major planets but still historically useful, travels at about 17 degrees to that plane. Those numbers are not large compared with the steep paths of many comets, but they are enough to correct the common drawing. The solar system is flat only in the softened sense that a wide field may seem flat when seen from far away. A reference plane can feel almost solid once it is drawn often enough. Diagrams encourage this feeling because a line on paper has a firmness that empty space does not. The planets appear as beads arranged along a track. The sun sits in the middle, and the page itself becomes a hidden flaw. In physical space, however, the plane is only a way of comparing one orbit with another. A planet above it now may pass through it later. A comet far below it may rise across it on the way inward. The plane remains still in the mathematics, while bodies continue their long circuits through and around it. Inclination is the name for that departure. It measures the angle between an object's orbital plane and the reference plane being used. A 0-degree inclination would mean that the orbit lies exactly in the chosen plane, while a steep inclination means that the orbit cuts across it at a slant. The 2 points where the orbit crosses the plane are called nodes, and those crossings matter in predicting where bodies may pass near other paths. This is not a decorative detail. The geometry of inclination helps distinguish the ordinary planet-like order of the solar system from the more scattered motions of asteroids, comets, and distant icy bodies. The reason many large planets share a similar plane lies deeper than their present orbits. It belongs to the way the solar system formed. The old nebula idea, associated in different forms with Immanuel Kant and Pierre-Simon Laplace, proposed that the sun and planets arose from a rotating cloud of material. In such a cloud, gravity gathered matter inward, while angular momentum preserved rotation. Motions that crossed one another could be damped through collisions and interactions, but the overall turning could not simply disappear. A flattened disk was therefore not an arbitrary arrangement. It was a consequence of a rotating origin. Laplace's version of the nebula hypothesis belongs to a period when astronomy was learning to explain not only where bodies were, but why their motions shared a family resemblance. The planets mostly travel in the same direction around the Sun. Their orbital planes are mostly close together. Their arrangement suggests formation from a common rotating system rather than separate placement one by one. The details of modern planetary formation differ greatly from Laplace's 18th century picture, but the central intuition remains recognizable. A disk is what a rotating, collapsing system tends to leave behind. The physical feeling of such a disk is not the feeling of a flaw. It is closer to motion losing some freedoms while keeping one. Material in a young cloud may begin with many directions, small swerves and crossings, clumps and unevenness, but repeated encounters make some motions less durable than others. The up and down components, measured relative to the growing average rotation, are softened by collision and exchange. The around the center component remains, because the system as a whole keeps its angular momentum. Over time, what was once a volume becomes a thinner region of shared circulation. Nothing in that process produces perfect thinness. A real disk has thickness, turbulence, heating, local concentrations, and later disturbances from growing planets. Some bodies are nudged into tilted paths, others are scattered outward or inward. Resonances alter orbits over long intervals, and encounters with giant planets can lift a small object away from the common sheet. The early flattening explains why the planets form a broad plane, but it does not imprison every object there. The solar system keeps the memory of a disk while also preserving the evidence of departures from it. This is why the question of what exists above and below the solar system cannot be answered by pointing to emptiness. Above and below the ecliptic, even close to the Sun, there are parts of orbits, not shelves of separate material. A planet may spend some of its path north of the reference plane and some south of it. An asteroid may cross it at two nodes. A comet may arrive from a direction so steep that the planetary plane seems almost incidental to its journey. The regions away from the ecliptic are not another solar system, but the same solar system seen in its fuller volume. The word north is sometimes used for one side of the ecliptic and south for the other, but these are extensions of a convention rather than discoveries of cosmic geography. Ecliptic north is defined by the direction of Earth's orbital angular momentum, the side from which Earth appears to move counterclockwise around the Sun. That definition is precise, and it is useful, but it is not universal. A different plane would produce different latitudes. The Milky Way has its own galactic plane, tilted with respect to the ecliptic, and the Sun's path through the galaxy introduces still another large-scale orientation. Astronomy is full of such agreements, each exact within its purpose and limited outside it. The planets, then, provide the first order of the solar system, while the chosen plane gives that order a language. Kepler's ellipses, Newton's gravity, and the nebular tradition all converge on the same quiet point. The solar system is not a stack of levels, but a family of motions with a shared inheritance. The ecliptic lets those motions be compared. Inclination reveals which bodies remain close to the old disk and which have been lifted, scattered, or preserved on steeper paths. Even before the asteroids and comets enter the chronicle, the flat diagram has already begun to thicken. Once that thickness is admitted, the origin of the plane becomes the next necessary question. A reference surface can describe where the planets travel now, but it cannot by itself explain why the largest bodies came to share that surface in the first place. For that, the chronicle has to move backward from finished orbits to the earlier cloud, where gravity, rotation, dust, and gas slowly turned a loose volume into a disk, and where the disk itself became the first lasting direction the solar system ever knew. Chapter 2: How a disk became a direction. Before the planets had names, and before their paths could be measured against the ecliptic, the solar system existed as a problem of motion inside a cloud. The finished orbits of Mercury, Venus, Earth, and the outer planets preserve only the later part of that story. Beneath them, in the older physical history, was a wide mixture of gas and dust that did not yet have planets inside it, only unevenness, gravity, and rotation. The plane that later became useful to astronomers began there, not as a line on a chart, but as the consequence of material gathering inward while still remembering how it turned. A cloud in space is not motionless because it looks diffuse. Every region inside it carries some small drift, some local turbulence, some inherited movement from the larger environment in which it formed. When gravity begins to gather such material together, the cloud contracts, and a faint rotation that once seemed almost negligible can become central to everything that follows. The same principle appears in a skater drawing in their arms. though the solar nebula was not a body with limbs and intention. As its material moved inward, its rate of turning increased, and the cloud's future became tied to the conservation of angular momentum. Immanuel Kant, writing in the 18th century, imagined that the solar system might have arisen from a dispersed original matter, a natural history rather than a finished architecture placed all at once. Pierre-Simon Laplace later gave the nebula idea a more mathematical form, proposing a rotating atmosphere around the young sun from which rings might separate and condense into planets. Modern planetary science no longer keeps Laplace's rings in that old form, but the underlying need his model answered remains. The planets move mostly in the same direction, near the same plane, and any account of their origin has to explain that shared behavior without treating it as coincidence. Laplace's attempt belongs to a time when celestial mechanics had made the heavens lawful, but not yet historical. Newton had shown how planets move under gravity, and Kepler had shown the shapes their orbits take, yet the question of why the system possessed its broad arrangement still remained. It was not enough to describe the motions one by one. The solar system seemed to have a memory older than any single orbit, a commonness of direction suggesting that the planets had not been assembled from unrelated beginnings. The nebula hypothesis offered a way to make that commonness physical. In a collapsing, rotating cloud, flattening is not an added feature. It is what remains after many other motions become harder to keep. Material can fall inward from different angles, but as particles, grains, gas streams, and clumps interact, motions that cross the average plane tend to be reduced. Collisions convert some organized motion into heat. Gas pressure redistributes energy. Dust grains settle and spiral. Through all of this, the total rotation of the system persists, so the cloud becomes wider around the direction of spin than it is along the axis of spin. The result is a disk, though the word can make the structure sound sharper and calmer than it was. A young protoplanetary disk is not a perfect sheet. It has thickness, temperature gradients, turbulence, magnetic effects, spiral features, local rings, and changing densities. Gas moves differently from dust, fine particles behave differently from larger solids, and the central young star is still gathering mass while its surroundings continue to evolve. Yet in the midst of that complexity, the disk supplies the lasting orientation. It defines the average plane in which most of the growing material will continue to circulate. The Atacama Large Millimeter Submillimeter Array, usually called ALMA, has made such disks visible with a delicacy earlier astronomers could not have approached. High on the Chajinantor Plateau in northern Chile, its many antennas work together as an interferometer, collecting millimeter and submillimeter light from cold dust and gas around young stars. In 2014, images of the young star HL Tau showed a disk marked by bright rings and darker gaps, a pattern that looked, to planetary scientists, like structure forming in the raw material around a star. The image did not show the solar system's own birth, but it made the idea of disk-borne planets feel less like a reconstruction from ruins and more like an observed process occurring elsewhere. HL Tau was young by stellar standards, still surrounded by material from its formation. The rings in its disk were measured at distances comparable to the realm of giant planets in our own system, and the gaps suggested that growing bodies or other disk processes might already be shaping the material. A single observation did not settle every detail, because disks can form rings through several mechanisms. Even so, the sight of a flattened, structured reservoir around a young star gave modern substance to the older thought that planetary systems begin as rotating matter rather than as isolated planets placed into finished paths. The sensory fact of a protoplanetary disk is almost unavailable to the body because its scale defeats ordinary comparison. Still, the physical process can be felt through the way motion becomes restricted. A loose volume gathers inward, and the directions that once crossed freely through it become less durable. Material that strays above the average turning plane meets other material, exchanges energy, and returns closer to the common flow. The rotation remains like a memory held by the whole cloud, not visible as a surface, but persistent enough that the future planets will inherit it. Dust begins its own slower history inside that flow. Tiny grains collide and sometimes cling, not because the process is smooth, but because innumerable encounters give growth many chances. Larger aggregates settle toward the midplane, where density is greater and collisions become more frequent. Planetesimals form through processes still studied in detail, including gravitational collapse within dense streams of solids and the gradual accumulation of material into kilometer-scale bodies. Once such bodies exist, gravity lets them gather more efficiently, and the disk becomes a nursery not only of dust and gas, but of objects large enough to alter the paths around them. The planets did not grow in a silent and perfectly ordered ring. Jupiter and Saturn accumulated great masses of gas and strongly shaped the smaller material around them. Uranus and Neptune formed in the outer system, and their later migration helped sculpt populations beyond them. In the inner region, rocky worlds grew through repeated impacts and mergers, leaving behind planets with different masses, spins, atmospheres, and histories. Yet their orbits retained the broad signature of the disk. Even after violence, loss, and rearrangement, the main planets continued to circle near the plane established when the solar nebula flattened. There is a quiet discipline in separating the origin of the plane from the later disturbances that complicated it. The disk explains why there is a dominant order, but not why every object follows it perfectly. Once planets grow, they cease to be passive products of the disk and begin to reshape the system that made them. Their gravity scatters smaller bodies, traps some in resonances, clears zones, and sends other objects onto tilted or elongated paths. The same disk that produced a flat architecture also produced the massive planets capable of bending many later orbits away from that architecture. This is why the solar system can be both disk-like and thick. The major planets preserve the old midplane because they carry the largest share of the system's organized orbital structure. Smaller bodies, being easier to disturb, record a more restless history. Some asteroids lean away from the ecliptic. Some comets approach along steep or even retrograde paths. Some trans-Neptunian objects travel through volumes far above and below the region occupied by the planets. Their inclinations are not failures of the disk model. They are the evidence that formation was followed by billions of years of gravitational editing. In the earliest disk, a grain of dust did not know that one direction would become north and another south. It moved according to local forces, gas drag, collisions, radiation, and gravity. Only later, when the system was large enough to be described from outside itself, could astronomers assign coordinates to the inherited order. The ecliptic became one plane because Earth's orbit made it convenient. The invariable plane, defined by the total angular momentum of the solar system, became another, slightly different and in some ways more physically representative reference. Each plane reveals a different aspect of the same old rotation. The invariable plane is especially useful because it is tied not to Earth's viewpoint, but to the system's total orbital angular momentum. Jupiter, because of its large mass and wide orbit, contributes strongly to that total. The ecliptic and the invariable plane lie close to each other, but they are not the same, and the difference is a reminder that every reference surface has a history behind it. Earth gives one useful plane, the solar system as a whole gives another. The young disk gave the material condition from which both became meaningful. A finished planetary system can look settled when drawn on a page, but its plane is the preserved outcome of a process that once involved gas drag, condensation, accretion, heating, cooling, migration, and the gradual clearing of space. Flatness is not simplicity. It is the visible remainder of many interactions that reduced some kinds of motion while preserving rotation around the young sun. The plane is therefore not merely where the planets are. It is a record of how a cloud became a system. From that record, the next layer of the chronicle follows naturally. If the disk made the broad direction, and if the planets kept most closely to it, then the smaller bodies reveal where that order was never complete. Between Mars and Jupiter, the first great population of such bodies appeared not as a planet, but as many fragments moving under the patient influence of resonances, gaps, tilts, and old collisions. The disk had given the solar system its plane. The asteroids would show how much could remain unsettled inside it. Chapter 3. The small bodies that refused the plane. Between Mars and Jupiter, the old disk did not gather itself into a single ordinary planet. Instead, it left a population of smaller bodies whose paths carried the memory of formation and disturbance together. The region looked, at first, like an absence. Kepler had noticed the wide gap between Mars and Jupiter, and later numerical patterns, especially the Titius-Bode relation, encouraged astronomers to expect something there. When a body was finally found in that space, it seemed briefly as though the missing member of the planetary family had appeared. The truth became stranger and more useful than that. On the first day of 1801, Giuseppe Piazzi, working in Palermo, observed a small object moving against the background stars. It was later named Ceres, after the Roman goddess associated with grain and fertility, and for a time it was treated as a planet. Its orbit lay in the gap that had drawn attention, and its discovery seemed to give the solar system a new completeness. Yet Ceres was too small and too alone in its category to hold that role for long. Within a few years, Pallas, Juno, and Vesta were also found, each occupying the same broad region between Mars and Jupiter, and the single missing planet became a swarm. Pallas changed the story in a particularly useful way. Discovered by Heinrich Wilhelm Olbers in 1802, it did not travel close to the ecliptic in the easy manner of most planets. Its orbit is tilted by more than 34 degrees, a steep inclination for a body in the inner architecture of the solar system. That angle gave the asteroid belt an immediate thickness in the mind, long before thousands and then millions of smaller bodies were known. A planet-like gap had not produced a planet-like answer. It had opened onto a region where small worlds crossed the shared plane at many slants. The early asteroid discoveries were made through patient comparison, not through spectacle. A point of light that had shifted from one night to another had to be separated from the fixed pattern of the stars. Its position had to be measured, its path calculated, its return predicted. Ceres itself was temporarily lost behind the Sun after Piazzi's first observations, and Carl Friedrich Gauss, still very young, developed methods that helped recover its orbit from limited data. There is something characteristic in that episode. A tiny body, faint and easily misplaced in the sky, required mathematics strong enough to restore it to the map. As more asteroids were found, their collective behavior became more important than any single object. They occupied a region, but not evenly. Their distances from the Sun showed patterns of crowding and absence, and their inclinations varied in ways that made the belt less like a ring than a thickened, structured population. Some stayed close to the ecliptic, others leaned noticeably away from it. The space above and below the solar system's main plane was therefore not occupied only by distant comets or outer icy bodies. Even between the familiar orbits of Mars and Jupiter, small rocky worlds were already passing through the plane at angles. Daniel Kirkwood gave one of the belt's absences its proper meaning. In the 19th century, he studied the distribution of asteroid orbits and noticed gaps at certain distances from the Sun. These were not accidental empty strips. They corresponded to orbital periods that formed simple ratios with Jupiter's period, such as the 3-to-1 resonance, where an asteroid would complete 3 orbits for every 1 orbit of Jupiter. Over time, repeated gravitational nudges at the same orbital relationship could alter a body's path, making that region less stable. The gap was a trace of Jupiter's timing. A resonance is a small persistence with large consequences. A single pull from Jupiter may be almost nothing to a small asteroid moving far away, but the same kind of pull repeated at the same phase of an orbit becomes a form of sorting. The body does not need to be seized by Jupiter or flung away in a single moment. Its orbit can be changed gradually, with eccentricity increasing, crossings becoming more likely, and the original path losing its long-term stability. The empty regions in the belt are therefore not emptiness without cause. They are the long afterimage of repeated gravitational rhythm. The same principle helps explain why the asteroid belt cannot be understood as leftover material sitting passively where a planet failed to form. Jupiter's gravity shaped the region from the beginning. Its mass stirred the velocities of smaller bodies, making gentle accumulation into a planet more difficult. Collisions between planetesimals could fragment rather than merge when relative speeds became too high. Later resonances removed material from particular zones and sent some bodies inward toward Mars, Earth, and Venus, or outward toward more complicated paths. The belt remained because it was both a remnant and an edited remnant. Inside that edited remnant, families of asteroids preserve another layer of history. When a larger body is broken apart by a collision, its fragments continue on related orbits, sharing elements that allow astronomers to recognize their kinship. The Hirayama families, named for the Japanese astronomer Kiyotsugu Hirayama, revealed that some groupings in the belt were not random gatherings, but the dispersed remains of older parent bodies. Their members may differ in size, brightness, and later surface history, yet their orbital similarities carry the signature of a common origin. In this way, the belt records not only where bodies are now, but how they separated. Inclination runs through these histories as a measure of disturbance and inheritance. A low-inclination asteroid remains close to the common planetary sheet, crossing above and below it only slightly during its orbit. A high-inclination asteroid spends much of its time far from that sheet, descending through it at one node and rising through it at the other. The ecliptic, again, is not a barrier. It is the plane against which the slant becomes visible. Without that reference, the orbit is merely a path in space. With it, the path becomes part of a larger comparison, and the belt's thickness can be described. The asteroid belt also contains different compositions, arranged broadly by distance from the Sun. Some inner belt asteroids are relatively stony, while many farther out are darker and richer in carbon-bearing material. This compositional gradient is not perfectly clean because the belt has been stirred for billions of years, but it still reflects conditions in the early solar system. Temperature, chemistry, water-bearing minerals, and later heating all left their marks. Above and below the plane, then, the belt is not only a set of tilted paths, it is a dispersed archive of rocky and carbon-rich material from different zones of the young disk. Vesta gives that archive a more tangible form. It is large enough to have differentiated, separating into crust, mantle, and core early in solar system history, and meteorites found on Earth have been linked to it through spectral evidence and dynamical pathways. The Dawn spacecraft, after orbiting Vesta and then Ceres, gave both bodies a closer modern history of measurement. Vesta's Great Southern Basin and Ceres' hydrated minerals belong to a later chapter of exploration than Piazzi and Olbers could have imagined, but they continue the same question. The small bodies between Mars and Jupiter are not uniform debris. They are worlds and fragments, each carrying a partial record. Ceres, now classified as a dwarf planet, remains the largest object in the belt. Its nearly spherical shape, low density compared with rocky planets, and evidence for water-bearing minerals make it unlike the brighter basaltic character associated with Vesta. Pallas, steeply inclined and difficult for spacecraft to reach, still holds its place as a reminder that the belt extends well away from the ecliptic. These three bodies alone would be enough to prevent the asteroid belt from becoming a simple ring in the imagination. One is hydrated and rounded, one is differentiated and scarred by ancient impacts, and one travels through the belt on a sharply tilted path. The near-Earth asteroid population carries material from these main belt source regions into more familiar space. Resonances and planetary encounters can move asteroids onto orbits that cross Mars's path and sometimes Earth's. These bodies are often described in terms of hazard, and the reason is understandable. But in the calmer language of celestial mechanics, they are also evidence of transport. The belt is not sealed. Its unstable zones feed other regions, and some of the objects that pass above or below Earth's orbital plane began as members of the older population between Mars and Jupiter. Their present nearness is part of a longer dynamical route. When an asteroid crosses the ecliptic, the crossing point itself can be calculated with precision, but the larger meaning lies in the orbit as a whole. The body is not visiting an upper or lower realm. It is following a path shaped by the Sun, Jupiter, Mars, previous collisions, radiation forces, and time. Its inclination may remain steady for long intervals or change under secular perturbations, the slow gravitational effects that accumulate as planets pull on one another and on smaller bodies. The belt is therefore not frozen. It is stable enough to persist, yet active enough to keep redistributing its members. The region between Mars and Jupiter shows, in a concentrated way, what the solar system did after the disk made its first order. The plane remained, but it did not command every body into obedience. Jupiter's gravity opened gaps, collisions made families, resonances moved small worlds into new paths, inclinations gave the belt volume. Above and below the ecliptic, the rocky remnants of formation continued to pass, carrying evidence that a flat beginning could lead to a thick and uneven present. From these rocky bodies, the chronicle naturally turns toward colder and longer paths. The asteroids show how the solar system's plane could be crossed and complicated from within by fragments left near the region of the planets. Comets carry the same lesson farther outward and make it steeper. Their orbits can lean sharply, reverse the common direction, and stretch so far from the Sun that most of their existence is spent beyond the ordinary planetary map. The belt revealed that the disk was never perfectly flat in practice. The comets will show how far a body can depart from that plane and still remain part of the Sun's extended order. Chapter 4. Comets coming down from steep angles. Comets carry the problem of inclination farther than the asteroids do. A rocky body between Mars and Jupiter may lean away from the ecliptic, crossing the planetary sheet with each orbit, yet still remain part of a region that seems broadly tied to the old disk. The comet can arrive from a much steeper path, sometimes from far above the planetary plane, sometimes from far below it, and sometimes moving in the opposite direction from the planets themselves. Its appearance near the Sun may last only weeks or months, but that brief inward passage belongs to an orbit whose full shape can reach across distances that make the ordinary planetary map feel small. For much of human history, comets did not seem to belong to order at all. Planets returned to recognizable paths, the moon repeated its phases, and the fixed stars held their relative patterns with patient regularity. Comets appeared differently. They brightened, lengthened, faded, and did not always come from the same part of the sky. Their tails changed with the sun's light, and their paths did not remain near the familiar band where the planets moved. Before their motion was understood, they looked like interruptions in the sky's settled habits, though the interruption was in human expectation rather than in nature. The change came through calculation. Edmund Halley, working with Newton's mechanics, compared the recorded appearances of comets in 1531, 1607, and 1682 and recognized that these were not three unrelated visitors. They were one body returning along a long elliptical orbit. Halley predicted that it would come back, and after his death, the comet did return, reaching perihelion in 1759. The success of that prediction did not merely attach Halley's name to a comet. It moved comets into the same gravitational language as planets, moons, and falling bodies, and it showed that a path could look disorderly only because its full period was longer than a human life. Halley's comet remains a useful object because its orbit refuses the polite arrangement of the major planets. Its period is roughly 76 years, and its path is steeply inclined to the ecliptic. More than that, it is retrograde, meaning it travels around the Sun in the direction opposite to the planet's usual motion. In orbital terms, its inclination is greater than 90 degrees, which marks it as a body moving against the inherited traffic of the solar system's disk. Nothing about that makes it outside the Sun's gravity. It is part of the solar system, but it preserves a different dynamical history from the planets. Retrograde motion has a special quietness in the mathematics. There is no signpost in space where the common direction becomes reversed, no turnstile at the edge of the planetary region. There is only a path whose angular momentum points the other way when compared with the reference plane. A comet on such an orbit may pass near the Sun with great speed, cross the ecliptic at a slant, and withdraw again into distance. The reversal is not dramatic in itself. It is a statement about origin, disturbance, and the long rearrangement of smaller bodies under the gravity of larger ones. Comets are often divided by period, though the boundary is a convenience rather than a wall. Short-period comets, especially those with periods under about 200 years, are usually connected with reservoirs shaped by the giant planets and the outer solar system. Jupiter family comets, many with periods under 20 years, have paths strongly influenced by Jupiter, and their inclinations tend to remain closer to the planetary plane than those of many long-period comets. Halley-type comets, with longer periods and often steeper inclinations, occupy a more complicated middle ground. Long-period comets can take thousands, tens of thousands, or even millions of years to return. The distinction matters because it begins to reveal what exists above and below the solar system. A short-period comet may have been drawn inward from the trans-Neptunian region, gradually altered by encounters with the giant planets until its orbit became small enough to revisit the inner solar system on a humanly noticeable interval. A long-period comet, by contrast, may arrive from a distant reservoir surrounding the Sun in a far more nearly spherical distribution. The difference between these sources will grow more important later, when the chronicle reaches the Oort Cloud. For now, the important point is that comet inclinations are not random decoration. They are clues to source regions. A comet spends most of its life in faintness. The bright head and tail that make it recognizable near the Sun are not its normal condition, but a temporary response to warmth far from the inner solar system. A cometary nucleus is a small body of ice, dust, darker organic-rich material, and frozen volatiles, only a few kilometers or tens of kilometers across in many cases. It can remain cold and inactive for most of its orbit, reflecting little sunlight and offering no tail at all. Then, as it approaches the Sun, ices begin to sublimate, gas escapes, dust is carried outward, and the coma forms around the nucleus. The tail does not trail behind the comet in the simple sense suggested by motion. Dust and ion tails respond to sunlight, radiation pressure, and the solar wind, so their direction depends strongly on the Sun rather than merely on the comet's path. The ion tail, shaped by charged particles and magnetic fields carried outward by the solar wind, points generally away from the Sun. The dust tail curves more gently because dust grains keep more of the comet's orbital motion. Even here, in the visible feature most associated with comets, the Sun's wider influence appears. The comet is not only an icy body on a steep path, it is also a temporary instrument revealing the environment through which it moves. The life of a long-period comet can be felt as a great imbalance of time. For almost all of its orbit, the body remains remote, cold, and small, traveling so far from the Sun that sunlight is weak and the planets are gathered into a distant center. Its inward passage is brief by comparison. The coma appears, the tail lengthens away from the Sun, the orbit bends through perihelion, and then the body begins to recede. What human observers notice is the short, warm fraction. What the orbit mostly contains is distance. This imbalance helps explain why comets once seemed so unpredictable. A body that returns every few thousand years does not easily enter human record as a return at all. Its previous passage may have occurred before written astronomy, before agriculture in some regions, or before the cultural memory that could connect one appearance to another. The comet arrives as a new object because the archive is too short, not because the orbit lacks continuity. Halley's great achievement was partly a victory over this shortness. He found sameness across separated records and allowed one comet to outlive the ordinary scale of historical attention. Some comet families bring the story closer to the Sun. The Kreutz sungrazers, for example, are understood as fragments of a larger comet that broke apart, leaving related bodies on paths that pass extremely near the Sun. Their orbits are steeply inclined, and many of the smaller sungrazers do not survive their close approaches. In a less careful register, such objects might invite fiery language, but the scientific truth is better held through outcome and geometry. A fragile, icy fragment follows a path inherited from an older body, approaches the Sun closely enough for heating and tidal stresses to matter greatly, and may dissolve into dust and gas before it can return. The sungrazers also show how comet paths can preserve family history. Just as asteroid families retain related orbital elements after an older body separates into fragments, comet groups can carry the signature of a common parent. The fragments do not need to remain close together in space for the relationship to persist in their paths. Their orbits become the genealogy. Above and below the ecliptic, a family can be dispersed across time, with one fragment passing near the Sun centuries apart from another, each briefly brightened by the same central star, each following a version of an older trajectory. Planetary encounters can change comet orbits with great subtlety or with lasting consequence. Jupiter is especially important because its mass gives it the power to shorten periods, raise or lower inclinations, or remove some comets from the inner system's repeating traffic. A comet approaching from the outer solar system may pass near Jupiter and leave with a different path, sometimes becoming a Jupiter family comet, sometimes being sent outward onto a longer orbit, sometimes being lost from the solar system entirely. The encounter itself may be brief, but its effect can remain written across many revolutions. These changes do not erase the older source story, but they complicate it. The comet observed today has a present orbit, a recent dynamical history, and a deeper origin that may not be recoverable with certainty. Non-gravitational forces add another layer, because jets of gas escaping from the nucleus can alter the comet's motion slightly, especially for smaller bodies. The surface changes with each passage near the Sun. Volatile material is lost. Dust mantles can form. Some comets fade into inactive bodies that look more asteroid-like. The boundary between categories, once again, is useful but not absolute. The steepness of a comet's orbit gives the solar system volume in a way the planets alone cannot. A diagram of the major planets seen from the side would show a narrow band with only small deviations from the chosen plane. Add long-period comets, and the picture becomes a set of narrow ellipses arriving from many directions. Some bodies cross the ecliptic near the inner planets. Others descend through the plane far away. Many spend most of their time at distances where the Sun is still gravitationally important, but no longer dominant in the everyday visual sense of brightness and warmth. At the crossing nodes, the comet enters the same reference surface that holds Earth's orbital path, though usually not at the same time or place. The mathematics can state the crossing exactly, but the physical orbit remains a three-dimensional curve through the Sun's gravitational field. Above and below are therefore not separate territories where comets reside permanently. They are portions of long paths, described relative to a plane that helps the observer understand the slant. A comet may be far above the ecliptic for an immense part of its orbit, and then pass through the planetary region almost like a needle through cloth, though the cloth itself is only a coordinate agreement. The more comets were measured, the more they pointed beyond themselves. Short-period comets suggested reservoirs in the outer planetary region. Long-period comets suggested a much more distant source, one that could send bodies inward from many directions rather than mainly along the old disk. This was the reasoning that would eventually lead Jan Oort to infer a distant cloud around the solar system. But the path to that inference runs through intermediate populations as well. Between the planetary region and the nearly spherical comet reservoir lies the broad outer terrain beyond Neptune, where icy bodies preserve the disk's old shape while also showing the effects of scattering. Comets therefore extend the lesson begun by the asteroids. The disk made a preferred plane, and the asteroids showed that small, rocky bodies could lean away from it while remaining shaped by planets and resonances. Comets make the departures colder, longer, and steeper. They carry the eye from the inner solar system toward reservoirs that are only partly visible, where a body may belong to the Sun while spending nearly all of its time far outside the familiar planetary arrangement. Their paths prepare the next question with unusual clarity. If some comets come from beyond Neptune, then the region beyond Neptune cannot be treated as empty space beyond the last planet. It must be a real province of icy bodies, resonances, migrations, and scattered orbits, thickening the solar system again at its outer edge. Chapter 5. The Belt that Thickens Beyond Neptune. If some comets come from beyond Neptune, then the last major planet cannot mark the end of the solar system in any simple way. Neptune is the outermost of the 8 planets, but its orbit lies inside a wider and colder region where small icy bodies preserve both the memory of the ancient disk and the consequences of later disturbance. The planets made the solar system look orderly because they are large, bright enough to be found early, and close enough to be followed across generations. Beyond them, the order continues, but it thins, spreads, and becomes harder to see. The question of what exists above and below the planetary plane therefore moves outward into a place where the old disk is still present, though no longer narrow. Pluto was the first sign that the outer system would not behave as neatly as the inner planetary list suggested. Clyde Tombaugh found it in 1930 after a careful photographic search at Lowell Observatory, comparing plates of the sky until a small point shifted against the fixed background stars. It was first accepted as a 9th planet, and for decades it occupied that role in school diagrams and public imagination. Yet Pluto's orbit was already unusual by planetary standards. It is more elliptical than the orbits of the major planets, and it is inclined by about 17 degrees to the ecliptic. Even before many similar bodies were known, Pluto quietly indicated that the region beyond Neptune did not lie flat in the same way as the main planetary family. That inclination mattered. Pluto crosses above and below the ecliptic during its long 248-year orbit, and its path is locked in a 3-to-2 resonance with Neptune, completing 2 orbits for every 3 of Neptune's. The resonance keeps the 2 bodies from close approaches despite the way their orbital distances overlap in projection. What looks dangerous in a flat drawing is stable in the fuller geometry of timing and inclination. The outer solar system was already teaching the same lesson in a colder register. Apparent crossings on a page do not tell the whole physical story. The idea that Pluto might not be alone did not begin with the late 20th century surveys. Kenneth Edgeworth and Gerard Kuiper both considered the possibility that material beyond Neptune could remain from the solar system's formation, though the details of their arguments differed and the modern population does not belong cleanly to either man's original picture. Their names became attached to the broad region now called the Kuiper Belt, a disk-like population of icy bodies beyond Neptune. For many years, however, this region was more expectation than catalogue. Astronomers could reason that small bodies should exist there, especially as a source for some short-period comets, but actually finding them was another matter. The recovery of that population came slowly, through repeated looking. David Jewett and Jane Liu began searching for distant objects beyond Pluto with the patience required by faint motion. In 1992, they found an object later designated 1992 QB1, a small world beyond Neptune that was neither Pluto nor Charon nor a comet already known by its inner passage. It was not visually grand, it was a faint moving point, yet its importance lay in category rather than brightness. After decades in which Pluto seemed nearly solitary, the outer solar system began to repopulate. Jewett and Liu's discovery altered the meaning of Pluto. A body once treated as an odd planet became one member of a larger trans-Neptunian population. More objects followed, and the Kuiper Belt became an observed region, not merely a proposed remnant. Some bodies moved on relatively low inclination, low eccentricity orbits, closer to the older idea of a cold classical belt. Others occupied resonances with Neptune. Still others followed more elongated and tilted paths, carrying the signature of scattering and migration. The belt did not erase Pluto's interest. It gave Pluto neighbors, and in doing so made its oddities more intelligible. A belt, in ordinary language, suggests a narrow band. The Kuiper Belt is better understood as a broad zone of icy bodies occupying a large volume beyond Neptune. Many of its members remain closer to the plane than long-period comets do, but the population is not a flat line. It has thickness, structure, resonant groups, and objects whose inclinations rise well above the easy expectations of a planetary diagram. A body with a tilted orbit spends part of its path north of the ecliptic and part south of it, crossing the chosen plane at its nodes. The belt therefore surrounds the planetary region not as a rigid rim, but as a sparse, cold, uneven continuation of the disk's old material. The cold classical Kuiper Belt preserves some of that older order. These bodies tend to have relatively low inclinations and less disturbed orbits, and they may retain information about the solar system's early outer disk. Their surfaces are darkened and reddened by irradiation and chemical alteration over long time, and many are small enough that their details remain difficult to measure from Earth. The coldness in the name refers to dynamical temperature rather than ordinary thermal cold, meaning that their orbits are less excited. Even so, the physical cold is also real. At 40 or more astronomical units from the Sun, sunlight is faint, and volatile materials can remain stable in ways impossible near the terrestrial planets. Beside this quieter population are resonant objects, whose paths are tied to Neptune's orbital rhythm. Pluto is the familiar example, but many bodies share the same 3:2 resonance and are sometimes called Plutinos. Others occupy different resonances, completing their solar circuits in ratios that keep their motions gravitationally organized over long intervals. Resonance does not require nearness at every moment. It requires repeated timing, a relationship that allows the same planetary influence to arrive in an ordered pattern. In the outer solar system, such timing can preserve bodies from disruptive close encounters even while their orbits appear, in a simple diagram, to cross dangerous regions. Neptune's migration is central to this story. In many models of early solar system evolution, Neptune did not form exactly where it now resides and remain unchanged. As the giant planets interacted with planetesimals, their orbits shifted, and Neptune's outward movement swept resonances through the trans-Neptunian region. Some bodies were captured, others were scattered. The outer disk was not merely left behind by formation, it was rearranged by the changing positions of the planets that had grown from the disk. The region above and below Neptune's plane therefore contains not only old material, but old material moved into new kinds of order. The scattered disk carries the more restless part of that inheritance. Its objects often have elongated orbits, with perihelia near enough to Neptune for the planet's gravity to have shaped them, and aphelia that carry them much farther outward. Their inclinations can be high, and their paths may lift them far above or below the ecliptic. These bodies are not arranged like a calm extension of the classical belt. They are the population left by encounters, near encounters, resonances, and long gravitational diffusion. In them, the solar system's flat disk has become a thicker and more erratic volume. A scattered object can spend most of its orbit far from the region where Neptune altered it. Near perihelion, it returns toward the planetary frontier where another interaction may eventually adjust its path. Farther out, it moves slowly through a dim region where the Sun still rules its orbit but offers little warmth. The felt structure is not a ring, but a wide, sparse weathering of paths. Some bodies pass through the ecliptic and climb away from it. Others remain inclined for vast intervals, crossing the old plane as a consequence of an orbit that no longer belongs neatly to the disk in which it began. Short-period comets connect this region with the previous chapter's story. Many Jupiter family comets are thought to originate from trans-Neptunian populations, especially the scattered disk, before gravitational interactions move them inward. An icy body beyond Neptune may not begin as a visible comet. It may spend long ages as a dark, frozen object, then be shifted gradually into an orbit that approaches the Sun more closely. Once it enters the inner solar system, warming makes its volatile materials active, and the body acquires the coma and tail by which observers recognize it. The comet's brightness is therefore a late episode in a much longer outer system history. This connection gives the Kuiper Belt and scattered disk a special place in the question of above and below. They are not simply regions beyond the known planets. They are source regions for bodies that later cross the planetary plane on steeper, shorter, or more altered paths. The icy object far beyond Neptune and the comet seen near the Sun may be the same body at different stages of dynamical life. Between those stages lies a chain of perturbations, resonances, and encounters, most of them too slow to be dramatic in any ordinary sense, but sufficient over time to move a small world from one category into another. Eris widened the outer system again. Discovered in 2005 by a team led by Mike Brown with Chad Trujillo and David Rabinowitz, Eris is massive enough to have forced a reconsideration of what the word planet should mean. Its orbit is highly inclined, roughly 44 degrees to the ecliptic, and elongated enough to carry it far beyond Pluto's average distance. The discovery did not simply add one more object to the catalogue. It showed that Pluto-like bodies, and even bodies comparable enough to challenge Pluto's classification, existed on paths well outside the thin planetary arrangement. The later reclassification of Pluto as a dwarf planet was not a demotion in the physical sense. Pluto did not change. Its mountains, nitrogen ice, moons, atmosphere, resonant orbit, and inclined path remained what they were. What changed was the category placed around it as the population beyond Neptune became better known. This is a useful kind of scientific adjustment because it shows the discipline of allowing names to follow evidence rather than asking evidence to protect familiar names. The outer solar system grew more complex and the language had to become more exact. Above and below the ecliptic, then, the trans-Neptunian region contains a layered mixture of order and disturbance. The cold classical belt preserves a low-inclination remnant of the ancient disk. Resonant populations keep time with Neptune. The scattered disk reaches outward and upward through elongated paths shaped by planetary encounters. Dwarf planets such as Pluto and Eris show that some of these bodies are large enough to become worlds in their own right, with moons, surfaces, volatile cycles, and histories that are not reducible to debris. The farther the chronicle moves from the Sun, the less the solar system resembles a tidy set of planets, and the more it resembles an extended archive of formation and rearrangement. Yet the Kuiper Belt and scattered disk do not exhaust the outer story. Some objects appear too detached, too distant at perihelion, or too peculiar in their orbital grouping to be explained only by ordinary Neptune scattering in its simplest form. Sedna, 2012 VP113 and related distant bodies will carry the chronicle into that more uncertain territory. The belt beyond Neptune has shown that the old disk thickens, breaks into populations, and feeds comets inward. The next step is to follow the bodies that seem to have moved beyond Neptune's ordinary reach, where the solar system's plane is still present as a reference, but no longer sufficient as an explanation. Chapter 6: The Scattered Disk and the Objects that Wander High. Some bodies beyond Neptune do not behave as though the planet still reaches them easily. They travel through the outer solar system on paths so long, so tilted, or so detached that the ordinary story of scattering has to be handled with care. Neptune shaped much of the trans-Neptunian region, and its gravity still governs the scattered disk in important ways. But farther out there are objects whose closest approaches to the Sun remain beyond Neptune's simple grasp. Their orbits are not numerous in the catalogue because such bodies are faint, slow, and difficult to find. Yet a few of them have changed the outline of the outer solar system more than their small points of light would suggest. The scattered disk itself is already a thickened region. Its objects often move on elongated orbits, with perihelia near Neptune's realm and aphelia that reach far outward into colder space. Their inclinations can be large, and their orbital periods can be measured in centuries or longer. A scattered disk object may return to the neighborhood of Neptune after spending most of its orbit at distances where the planet is only a remote gravitational actor. The term scattered does not mean random. It means that these bodies carry the history of gravitational encounters, especially with Neptune, that lifted and stretched their paths away from the older disk. Eris is one of the clearest examples of how the outer solar system resisted the old planetary list. Discovered in 2005 by Mike Brown, Chad Trujillo, and David Rabinowitz, it is a distant dwarf planet with an orbit inclined by roughly 44 degrees to the ecliptic. That angle alone places Eris well outside the ordinary thinness of the planets. Its path is also highly elongated, taking it from a perihelion beyond Pluto's distance to an aphelion nearly 100 astronomical units from the Sun. Eris did not merely add a new world beyond Neptune, it made the classification of Pluto impossible to preserve without asking language to ignore the population that observation had revealed. The discovery of Eris belongs to a modern form of patience. Instead of the eye at an eyepiece, there were digital surveys, repeated images, software comparisons, and careful searches for points that shifted against the background stars. The sky was no longer only looked at, it was revisited by data. Brown and his collaborators found several distant bodies in this way, and each one helped make the outer system less like a frontier beyond a final planet and more like a wide, structured territory with its own families. The faintness of these objects did not make them scientifically small. In astronomy, a single slow-moving point can force the rearrangement of a category. Sedna carried the difficulty farther. Announced in 2004 by a team led by Mike Brown, with Chad Trujillo and David Rabinowitz, Sedna followed an orbit unlike the ordinary scattered disk paths then familiar. Its perihelion lies around 76 astronomical units from the Sun, far beyond Neptune's 30 astronomical units, while its aphelion extends to hundreds of astronomical units. That means Sedna never comes close enough to Neptune for present-day encounters with the planet to explain its orbit in a straightforward way. It is not merely far at the outer end of its path, it is far even at its nearest. A detached orbit has a particular stillness in the mind. The body returns, but not to the planetary shore. It comes inward only to a remote distance, turns through perihelion in a dim region beyond Neptune's easy reach, and then recedes again along a path that takes thousands of years to complete. The Sun remains the central mass, the orbit remains bound, and yet the body spends its life in a region where the familiar planets no longer feel like immediate neighbors. The ecliptic can still measure the tilt, but it cannot explain the history. The path itself asks what past disturbance placed the object there. Sedna's orbit opens several possibilities, none of them requiring drama and none of them settled by the discovery alone. Perhaps the young sun formed in a cluster where another star passed near enough to lift distant objects into detached paths. Perhaps an early population of massive bodies beyond Neptune scattered objects before the system settled into its present form. Perhaps the galactic tide, weak but persistent across very large distances, played some role at the farthest parts of such orbits. Or perhaps an undiscovered planet in the distant solar system influenced the arrangement. Each possibility belongs to real dynamical reasoning, but each carries a different burden of evidence. The discovery of 2012 VP113 strengthened the sense that Sedna was not alone in its category. Found by Chad Trujillo and Scott Shepard, the object has a perihelion beyond 80 astronomical units, again too distant for ordinary encounters with Neptune to dominate its present orbit. Its discovery suggested that a population of inner Oort Cloud or detached trans-Neptunian bodies might exist, though only the brightest or most favorably placed members are currently detectable. A few points, carefully measured, began to imply a much larger unseen population. As often in astronomy, the known objects were not the whole structure, but the visible tips of a distribution. These discoveries made the phrase above and below more complicated. A scattered disk body can rise high above the ecliptic because Neptune altered its orbit. A detached object may also be inclined, but the cause of its detachment may belong to an earlier or more distant influence. Inclination, perihelion distance, aphelion distance, and orbital longitude all become pieces of the same slow puzzle. No single number gives the answer. A high inclination says that a path tilts away from the reference plane. A large perihelion says that the body does not return to Neptune's neighborhood. The distant aphelion says that the object spends most of its time in a realm where small perturbations can accumulate over immense intervals. One of the most discussed interpretations of some distant object orbits is the Planet 9 hypothesis. In 2016, Konstantin Batchin and Mike Brown proposed that the apparent clustering of certain distant trans-Neptunian orbits could be explained by a still unseen planet several times the mass of Earth, traveling on a long orbit far beyond Neptune. The hypothesis is not the same thing as a discovery. It is a proposed gravitational explanation for patterns in a small and observationally biased sample. Searches have continued, constraints have changed, and alternative explanations have been studied. The correct register here is neither dismissal nor certainty. It is a careful recognition that a possible planet is one way of accounting for some of the structure, not a body already added to the solar system. There is a quiet lesson in that distinction. Astronomy has often inferred unseen things before seeing them directly, and sometimes the inference has been vindicated. Neptune itself was found after irregularities in Uranus's motion led mathematicians toward a predicted position, yet history does not make every inference true by resemblance. Distant object clustering may point toward a planet, toward observational selection, toward collective effects, toward earlier stellar encounters, or toward some combination not yet fully understood. The outer solar system has room for hypotheses, but it does not need certainty before it can be studied. Observational bias matters strongly at these distances. Astronomers are more likely to find objects near perihelion, where they are closer to the Sun and brighter to telescopes. Surveys cover some parts of the sky more deeply than others. The Milky Way's crowded star fields can make faint moving objects harder to detect. Weather, telescope scheduling, instrument sensitivity, and the object's own surface reflectivity all influence discovery. The catalogue is therefore not a neutral sample of everything that exists. It is a shaped sample, and any pattern inside it has to be tested against the ways the sample was made. Even with those cautions, the distant detached bodies carry real information. Their orbits are long enough to preserve dynamical histories that may reach back to the Sun's birth environment. If the young Sun formed near other stars, as many stars do, then close stellar passages in the early cluster could have rearranged the outskirts of the solar system before the Sun drifted into its present galactic neighborhood. A passing star would not need to disturb the planets to alter far more distant small bodies. The weaker the Sun's grip at a given distance, the easier it becomes for outside influences to leave a lasting trace. The boundary between the scattered disk, detached objects, and the inner edge of the Oort Cloud is not a sharp surface. It is a classification problem built from orbits, source histories, and incomplete observation. Some bodies may have been scattered by Neptune and then lifted farther away by other effects. Some may belong to a fossilized inner Oort cloud, preserving early disturbances from the Sun's birth cluster. Others may occupy transitional paths that do not fit any clean label. The farther the chronicle moves outward, the more the solar system becomes a set of overlapping dynamical populations, rather than a set of named zones. A distant object on a detached orbit spends almost all of its existence beyond direct human intuition. Its motion near aphelion is slow. The Sun is still the dominant body, but its light is reduced to a small brightness, and its gravity holds the object with a gentler authority than it holds the planets. Over many centuries, the body changes position only gradually against the stars. If it is found at all, it is found because a survey returns to the same sky and notices that one faint point has not remained quite fixed. The discovery is a measurement of patience as much as distance. There are likely many such bodies still unseen. Some may be too small, too dark, too distant, or too poorly placed in their orbits for present surveys to detect. Others may await deeper wide-field instruments that can find slow movement across large areas of sky. The Vera C. Rubin Observatory, with its legacy survey of space and time, is expected to increase the known inventory of distant solar system objects substantially. Such discoveries may sharpen the evidence for clustering, weaken it, or replace current categories with better ones. The outer solar system is not finished in the catalogue, because the catalogue is still catching up with the volume. The high and detached objects also prepare the mind for a larger source of comets. If Sedna and 2012 VP-113 occupy a region sometimes associated with the inner Oort Cloud, then the solar system's distant structure is not merely a flat disk fading outward. It may include populations arranged through wider volumes, some still linked to the old planetary plane, some only loosely connected to it, and some perhaps distributed around the Sun in a much more spherical way. The scattered disk thickens the old disk. The detached objects begin to loosen it from disk-like thinking altogether. Above and below the ecliptic, then, the distant solar system contains more than comet paths passing through from an unseen reservoir. It contains dwarf planets on steep orbits, scattered icy bodies shaped by Neptune, detached objects whose present paths seem to preserve older or more distant disturbances, and possible populations that remain mostly invisible. These bodies are small compared with planets, but they are not incidental. They are the evidence that the solar system's outskirts were shaped by migration, resonance, scattering, stellar environment, and time. The plane that began as the disk's inheritance is still useful here, but it has lost its power to make the outer system feel simple. Inclination can say how far a path tilts. Perihelion can say how close it returns. Aphelion can say how distant its slow outer arc becomes. None of those measurements alone can say where the solar system ends. For that, the chronicle has to change the meaning of boundary itself. Beyond the scattered and detached bodies, the next structure is not defined by an orbiting population, but by the Sun's own outward breath, a moving region of charged particles and magnetic field that surrounds the planets, the belts, and the distant paths together. Chapter 7. The Bubble Around the Sun. Beyond the scattered and detached bodies, the solar system changes its kind of boundary. An orbit can show where a body travels, and a population can show where many bodies have gathered. But the Sun also makes a surrounding region by flowing outward. This region is not drawn by planets, comets, or dwarf worlds. It is shaped by charged particles leaving the Sun, by magnetic field carried with them, and by the pressure of the interstellar medium pressing back from outside. The structure is called the heliosphere, and it encloses the known planets, the asteroid belt, the Kuiper Belt, the scattered disk, and the long paths of many comets inside a moving solar atmosphere. Eugene Parker gave the solar wind its modern physical form. In the late 1950s, he argued that the Sun's outer atmosphere could not remain static, because a hot corona would expand outward into space. The idea met resistance, partly because it described interplanetary space as filled by a continuous solar outflow rather than as a calmer emptiness between worlds. Parker's mathematics did not require the Sun to release occasional material only during visible storms. It required an ongoing wind, thin by earthly standards, but persistent enough to fill the planetary region. Later spacecraft measurements confirmed that the Sun was indeed sending plasma outward past Earth and beyond. The word wind is useful, but it can mislead if it borrows too much from weather near the ground. The solar wind is not air, and it does not move through space as a gust through trees. It is a flow of charged particles, mainly protons and electrons, streaming away from the Sun through the solar system. Because those particles are charged, they carry and respond to magnetic fields. The Sun rotates as the wind moves outward, so the magnetic field becomes drawn into a broad spiral form, often called the Parker spiral. Even the space between planets, which seems empty in the eye's imagination, is crossed by this tenuous, structured outflow. This outflow gives the solar system a boundary unlike the boundary of a solid object. The heliosphere is the volume where the solar wind and the Sun's magnetic influence dominate over the surrounding interstellar medium. Its size is not fixed in the simple way a planet's radius is fixed. It changes with solar activity, with direction, and with the character of the material through which the sun is moving. The planets orbit well inside it. The Kuiper Belt lies inside it too. Some distant cometary reservoirs may extend far beyond it because the sun's gravity reaches much farther than the solar wind can hold its pressure. The outer heliosphere is described through several regions. First comes the supersonic solar wind, moving outward faster than waves in that plasma can communicate changes back toward the sun. Farther out, the wind slows at the termination shock, where it begins to feel the pressure of the material beyond. Beyond that lies the heliosheath, a broad, disturbed region where the slowed solar wind continues outward in altered form. Still farther is the heliopause, the boundary where the solar wind's pressure and the surrounding interstellar medium meet. It is not a wall, it is a contact between flows. A boundary like that has to be imagined without hardness. Inside it, particles from the sun have thinned across billions of kilometers, but they still carry the identity of their source. Outside it, interstellar plasma and magnetic fields belong to the galaxy's local medium rather than to the solar wind. At the heliopause, neither side becomes a surface that could be touched. Instead, pressure, particle density, temperature, and magnetic field direction change. The crossing is real because instruments can measure it, and unreal only if a boundary is expected to behave like a shore. Voyager 1 and Voyager 2 gave that boundary a history in measurement. Launched in 1977, they were built first for the grand tour of the outer planets, using gravity assists to visit Jupiter and Saturn, and in Voyager 2's case, Uranus and Neptune as well. After the planetary encounters, both spacecraft continued outward along different trajectories, no longer returning toward the sun. Their instruments aged, their power declined, and their distance grew into a scale that ordinary travel language cannot hold easily. Yet, they kept sending data, and the mission slowly became less a tour of planets than a probe of the sun's outer influence. Voyager 1 crossed the heliopause in 2012. Voyager 2 crossed it in 2018. These crossings were not marked by a camera image of an edge because there was no visible rim to photograph. They were recognized through changes in particles, plasma behavior, and the surrounding environment. The count of solar particles declined. Galactic cosmic rays became more abundant. Plasma wave measurements helped infer the density of the medium around the spacecraft. What had once been a theoretical boundary became a sequence of instrumental signs arriving across radio signals from far beyond the planets. Ed Stone, who served for decades as project scientist for the Voyager mission, became one of the steady human figures through whom these measurements entered public knowledge. His role was not to turn the spacecraft into myth, but to help translate faint, distant signals into a coherent account of where the machines were and what they had crossed. The long duration of the mission matters scientifically. A short mission can capture an encounter. A mission lasting across generations can watch the meaning of its own destination change. Voyager began with planets and continued into plasma boundaries. The heliosphere also changes the question of above and below. The ecliptic is still a useful reference plane, and Voyager trajectories can be described relative to it, but the heliosphere itself is not arranged like the planetary disk. The solar wind flows outward in all directions, while the sun moves through the local interstellar medium. The pressure outside is not identical in every direction, and the solar magnetic field adds further structure. For this reason, the heliosphere is often described as asymmetric, shaped by the sun's motion, the interstellar magnetic field, and the long breathing changes of solar activity. Above the planetary plane then, the sun's influence is not empty. Below it, the same is true. In every direction, charged particles have moved outward, becoming thinner with distance, but still helping define the region around the sun. A comet on a steep orbit passes through that environment. A spacecraft leaving the plane travels through it. Cosmic rays entering from outside are modulated by it. The heliosphere is a kind of surrounding weather, though too thin and too large for the ordinary senses, and it gives the solar system a physical volume that is not the same as the volume defined by orbiting bodies. The solar cycle adds another layer to this boundary. Over roughly 11 years, the Sun's magnetic activity rises and falls, changing the strength and structure of the solar wind, the number of sunspots, and the conditions that spread outward through interplanetary space. Coronal mass ejections and faster solar wind streams can move through the heliosphere, changing particle conditions far from the Sun. These variations do not redraw the heliopause in a simple, immediate way, because the heliosphere is vast and responses take time to move outward. Still, the boundary is not a frozen shell. It is sustained by a star that changes. The Parker Solar Probe, named for Eugene Parker, travels much closer to the Sun than the Voyagers ever did, entering the outer corona and measuring the young solar wind near its source. Its work belongs to the inner end of the same story, near the Sun. The wind is being accelerated, structured, and released. Far away, Voyager measures what that long flow becomes after crossing the planetary system and meeting interstellar space. The two perspectives are separated by immense distance, but the physical process joins them. A particle environment born near the corona helps make the bubble that surrounds the solar system. There is a useful restraint in remembering that the heliopause is not the edge of the solar system in every sense. The Sun's gravity reaches far beyond it, holding distant comets in orbits that may extend through and past the boundary of the solar wind. The Oort Cloud, if described by gravitational membership, belongs to the Sun even though much of it lies beyond the heliosphere. A spacecraft crossing the heliopause has entered interstellar space in the plasma sense, but it has not escaped the Sun's gravitational domain. Leaving in astronomy depends on what kind of belonging is being measured. This layered belonging prevents the solar system from having one clean edge. Neptune is the last major planet, but not the last body. The Kuiper Belt and scattered disk extend beyond Neptune, but not to the end of the Sun's gravity. The heliopause marks the outer reach of the solar wind's dominance, but not the outer limit of cometary orbits. The Oort Cloud, inferred from long-period comets, may extend far beyond the heliopause, but it is not a boundary that any spacecraft has yet entered and mapped. Each edge answers a different question, and none cancels the others. The heliosphere is therefore a middle kind of answer to what exists above and below the solar system. It is not a population of worlds, and it is not an empty direction away from the planets. It is a surrounding magnetic and plasma structure, made by the Sun and shaped by the galaxy around it. It contains the planetary plane inside itself, but does not copy that plane's flatness. It reaches outward in every direction, altered by motion and pressure, and its boundary can be crossed without ever seeing a surface. Once the boundary can be crossed, it can also be mapped. Voyager measured the heliosphere along two rare paths, but two paths cannot reveal the whole shape of a surrounding volume. To understand what lies above and below the Sun's bubble, astronomers needed particles arriving from many directions, carrying signs of distant interactions back toward Earth. The next chapter follows that quieter kind of mapping, where the edge of the solar system began to appear not through ordinary light and not through a spacecraft camera, but through neutral atoms returning from the boundary with the memory of where they had been. Chapter 8. The Ribbon at the Boundary. Neutral atoms made the heliosphere visible in a different way. Voyager had crossed the outer boundary along two narrow paths, and those crossings mattered because they turned a predicted region into measured plasma, measured particles, and measured change. The two spacecraft, however patient, could not describe the whole surface around the Sun. The heliosphere is a surrounding volume, shaped differently in different directions, and its form could not be recovered from two lines alone. To know more about what exists above and below the Sun's bubble, astronomers needed a method that could gather messages from the boundary itself. The Interstellar Boundary Explorer, known as IBEX, was built for that kind of indirect seeing. Launched in 2008, it did not travel to the heliopause as Voyager did. It remained much closer to Earth in a highly elliptical orbit and looked outward. Its instruments detected energetic neutral atoms, particles that had once been charged ions but had exchanged charge with neutral atoms and become electrically neutral. Once neutral, they were no longer guided in the same way by magnetic fields. They could travel in straight paths over immense distances, carrying directional information back from regions where the solar wind and interstellar medium interacted. This method is quiet in its logic. A charged particle is tied to electromagnetic structure, curved and guided by fields that make its path difficult to trace backward simply. A neutral atom, having lost that electrical attachment, can cross space more directly. When such atoms arrive near Earth from the outer heliosphere, their direction of arrival becomes a clue to the place where they were formed. Ibex did not photograph the boundary in reflected sunlight. It made a map from arrivals, counting particles from different directions until the invisible edge of the sun's influence began to acquire pattern. David McComas and the Ibex team expected to learn about the heliosphere's global interaction with interstellar space. They did not expect the first maps to contain the feature that became known as the Ibex ribbon. Across the all-sky map of energetic neutral atom emissions, a bright, narrow, winding band appeared. Unlike the smoother distribution many models had anticipated, it did not correspond to an ordinary visible structure, and it was not a ribbon made of material in the familiar sense. It was a region of enhanced energetic neutral atom flux, a pattern in particle arrivals that pointed towards something organized at or beyond the heliosphere's boundary. The word ribbon gives the feature a visual softness, but the scientific object is more exact than the word. It is a distribution in energy and direction. It is measured through particle counts, instrument calibrations, repeated observations, and comparison with models of magnetic fields and charge exchange. Its shape appears projected across the sky, but the processes that generate it unfold across a three-dimensional boundary where solar particles, interstellar atoms, and magnetic fields meet. Like the ecliptic, the ribbon can mislead if it is treated as a literal object. It is better understood as a trace of interaction. At the boundary, particles are continually changing their membership. Some solar wind ions move outward into the heliosheath. Some interstellar neutral atoms enter the heliosphere because they are not strongly guided by magnetic fields. When an energetic ion takes an electron from a neutral atom, the ion becomes an energetic neutral atom and may travel away from the site of exchange. If its path leads inward, an instrument like Ibex can detect it. The particle has not carried a message in any intentional sense, but its energy and direction preserve part of the physical condition from which it came. A boundary inferred this way has a different texture from one measured by a passing spacecraft. Voyager gave changes along a path, particle rates rising or falling, magnetic field behavior, plasma density inferred from waves. Ibex gave a sky. Its map did not show mountains or clouds, but it showed anisotropy, the unevenness of particle arrivals. One part of the sky sent more energetic neutral atoms than expected. The heliosphere, once imagined in relatively simple forms, had to be reconsidered in relation to the local interstellar magnetic field and the way that field drapes around the solar system's moving bubble. Magnetic draping is a phrase that can sound too material, as though a cloth had been laid over a surface. The actual process involves field lines in plasma shaped by the motion of the heliosphere through the surrounding medium. As the sun moves through local interstellar space, the external magnetic field interacts with the boundary, influencing how particles move and where energetic neutral atoms may be produced. The ribbon appears to be associated with directions related to that interstellar magnetic field, though its precise origin has been studied through several models. The important point is that above and below the planetary plane, the larger structure is not governed mainly by planets at all. It is governed by flows and fields. Here the old reference plane recedes. The ecliptic remains useful for describing spacecraft paths and planetary orbits, but the heliosphere responds to another set of orientations: the sun's rotation, its magnetic field, the interstellar magnetic field, and the sun's motion through the local medium all matter. A direction high above the ecliptic may be ordinary or unusual depending on which physical structure is being considered. The ribbon made this clear by refusing to behave like an extension of the planetary map. It belonged to the boundary between the solar and interstellar environments, not to the flatness of the planets. The sensory equivalent of such mapping is not the sight of a line, but the receipt of faint arrivals from many directions. Particles that began as part of a distant interaction travel inward without glowing, without announcing a surface, without carrying an image. They reach an instrument, are counted, sorted by energy and direction, and slowly become a map. The body has no natural sense for this kind of knowledge. It must be made by patience, by detectors, and by the willingness to let an invisible structure reveal itself through what arrives from it rather than through how it looks. Ibex also showed that the heliosphere changes. Energetic neutral atom emissions vary with the solar cycle because the solar wind itself changes over time, and those changes propagate outward before influencing the boundary regions from which neutral atoms return. The map is therefore not a single permanent portrait. It is a set of measurements across time, shaped by a star whose activity rises and falls. The heliosphere is maintained continuously, not established once. Its boundary carries the delayed history of solar variations, arriving at Earth after the outward flow has crossed great distance and after neutral atoms have traveled back. The ribbon's discovery also made clear how much remained uncertain. Several explanations were proposed, involving the local interstellar magnetic field, secondary energetic neutral atoms, particle distributions outside the heliopause, and the geometry of charge exchange. The uncertainty did not weaken the measurement, it gave the measurement work to do. A good observation often does not close a subject immediately. It rearranges the questions so that later instruments can ask them with more precision. The Interstellar Mapping and Acceleration Probe IMAP belongs to that later effort. Designed to study the heliosphere's interaction with the local interstellar medium in greater detail, it extends the same basic ambition that made IBEX so valuable. It is not a mission to the edge in the Voyager sense. It is a mission to receive the edge from afar, to measure energetic neutral atoms, interstellar particles, solar wind structures, and related phenomena with improved sensitivity and broader capability. The boundary around the solar system is so large that one way to study it is not by going there, but by learning to read what returns. There is a calm reversal in that method. The edge of the solar system, which seems far beyond reach, sends evidence inward. The instrument near Earth does not need to cross the heliopause to participate in its study. It waits in the inner system while particles created far away arrive from different directions. The map grows out of returns. In that sense, the heliosphere is not only a region the Sun makes outward, it is also a region whose outer interactions fold back into the inner solar system as measurable traces. Cosmic rays are part of the same surrounding story, though they are not the same as energetic neutral atoms. Galactic cosmic rays enter the heliosphere from outside, and the solar wind and magnetic field modulate how many reach the inner solar system. During different phases of solar activity, that modulation changes. The heliosphere therefore acts as a partial shield, not a perfect enclosure, reducing and shaping the arrival of high-energy particles from the galaxy. Above and below the planetary plane, this shielding does not follow the planet's flat arrangement. It belongs to the global plasma environment around the Sun. The heliosphere's asymmetry remains one of its most important features. Earlier images sometimes portrayed it like a comet-shaped bubble, with a long tail streaming behind the Sun's motion through interstellar space. Later work suggested a more complex form, and models have differed on whether the heliosphere possesses a long tail, a shorter, more rounded shape, or lobed structures influenced by magnetic fields and solar wind behavior. The exact global shape is still an active subject. What matters for this chronicle is that the solar system's boundary is not a clean sphere centered on a diagram. It is a negotiated structure made by pressure balance, fields, particle populations, and motion through the galaxy. Above the solar system, if above means north of the ecliptic, the heliosphere continues. Below it, the heliosphere continues as well. But its shape in those directions is not determined by the ecliptic itself. A person asking what exists there is no longer asking about planets or belts alone. They are asking about the sun's extended atmosphere, about particles that have thinned almost beyond ordinary imagination, about the local interstellar magnetic field, and about the ways a star moving through galactic material makes a boundary around itself. The answer has become less like a map of objects and more like a physics of contact. IBEAX gave that contact a pattern, and Voyager gave it crossings. Together, they changed the heliopause from a theoretical outer condition into a measured region with direction, variation, and texture. Yet the heliopause is still not the final reach of the sun. The solar wind weakens there, but gravity continues far beyond it. Long-period comets point to a reservoir outside the heliosphere's plasma boundary, a distant population that cannot be mapped by energetic neutral atoms and has not been visited by spacecraft. To follow what lies beyond the sun's bubble, the chronicle must leave the boundary of solar wind behind and return to orbits, but now on a scale so large that the old disk begins to loosen into a cloud. Chapter 9. The cloud that may surround everything. Beyond the sun's bubble, the solar wind no longer gives the solar system its main boundary. The heliopause marks the place where the outward flow of solar plasma yields to the surrounding interstellar medium, but the sun's gravity continues past that contact into a much larger and more weakly held realm. There, if the reasoning from long-period comets is correct, the solar system is not shaped like a disk in any ordinary sense. It becomes a vast, sparse reservoir of icy bodies, distributed so broadly around the sun that comets can arrive from many directions, not only from the old plane of the planets. This inferred region is called the Oort Cloud, and it changes the meaning of above and below again. The Oort Cloud has never been seen as a cloud. No telescope has resolved it as a shell around the sun, and no spacecraft has entered it with instruments ready to count its members. Its existence comes from the orbits of comets, especially long-period comets whose paths suggest that they began their inward journeys from very great distances. In that sense, it is one of astronomy's larger acts of inference. The bodies themselves are mostly too small, too dark, and too far away to observe directly where they spend most of their lives. Yet a few of them fall inward, brighten near the sun, and carry the geometry of their source with them. Ernst Öpik proposed in the early 20th century that long-period comets might come from a distant reservoir surrounding the solar system. Jan Oort, working later with cometary orbits, developed the idea in the form that became widely attached to his name. In 1950, Oort examined the distribution of long-period comet orbits and argued that many appeared to have come from an immense distance, from a region where the sun's hold was still present but faint enough for outside influences to matter. The comets did not behave as though they had all been stored in the flat planetary disk. Their directions suggested something more nearly spherical. Oort's reasoning began with returning bodies, not with a visible shell. A long-period comet near the sun has already been altered by the journey that made it observable. It may have felt the gravity of planets as it passed inward. It may have lost volatile material, changed its brightness, or had its orbit modified by non-gravitational forces from escaping gas. Even so, when enough comet orbits are examined, a pattern emerges. Many seem to have original orbits stretching outward to tens of thousands of astronomical units. They arrive from all over the sky, as though the source population surrounds the sun rather than lying mainly along the ecliptic. The scale is difficult to keep in ordinary thought. 1 astronomical unit is the average distance from Earth to the sun. Neptune orbits at about 30 astronomical units. The Kuiper Belt occupies a region beginning beyond Neptune and extending through dozens of astronomical units, with scattered objects reaching much farther. The Oort Cloud, by contrast, may extend from thousands of astronomical units to perhaps 100,000 astronomical units or more, depending on how its inner and outer parts are defined. At such distances, the Sun is still the central body for these icy worlds, but its authority is gentle, and the galaxy begins to participate in their motion. A body in the Oort Cloud is not waiting at the edge of a map. It is moving, slowly, on a bound orbit around the Sun, though its period may be measured in hundreds of thousands or millions of years. Its surface is cold, darkened, and largely unchanged by the Sun's warmth except during rare inward passages. Around it there is no bright planetary neighborhood, no dense belt, no visible boundary. The object remains one faint member of an enormous and diffuse population, separated from its neighbors by distances so large that the word cloud can almost exaggerate the density. It is a cloud because of distribution, not because of closeness. The Oort Cloud is usually divided conceptually into an inner part and an outer part. The inner Oort Cloud, sometimes associated with a more flattened or torus-like distribution in some models, may overlap in thought with the region hinted at by bodies such as Sedna. The outer Oort Cloud is more nearly spherical in the standard picture, and it is from this outer reservoir that stellar passages and galactic tides can more easily send comets inward. The distinction is not a wall. It is a way of describing how the Sun's distant comet reservoir may change character with distance, from a region still partly linked to the solar system's early plane to one more broadly distributed around the Sun. Galactic tides become important because the Sun does not sit alone. It moves through the Milky Way, surrounded by the galaxy's gravitational field. That field is weak across the scale of the planetary system, but across the enormous orbits of distant comets, it can slowly alter perihelia, lifting or lowering the closest points of their paths. A comet that once remained safely far from the planets may, after long perturbation, have its orbit adjusted enough to fall into the inner solar system. The change need not be sudden. It can accumulate across intervals so long that the movement seems less like an event than like a condition. Passing stars also matter. Most pass too far away to disturb the planets in any serious way, but the Oort Cloud is so large and so weakly bound that a star passing within a few light years can alter the orbits of some distant comets. The effect depends on distance, mass, speed, and direction. A close passage may send some bodies inward and others outward, slightly reshaping the reservoir. The planets remain almost untouched because they are held tightly by the Sun, but the outer comet cloud is sensitive to these faint galactic encounters. At the farthest scale of the solar system, the neighborhood of stars becomes part of the system's weather. This is one of the reasons the Oort Cloud carries the memory of the Sun's larger environment. If the Sun formed in a cluster, as many stars do, early stellar neighbors may have helped populate or reshape the distant reservoir before the Sun drifted into its present surroundings. Some comets may have formed closer to the giant planets and then been scattered outward by Jupiter, Saturn, Uranus, and Neptune during the solar system's youth. Once sent into large orbits, they could be lifted and randomized by external perturbations. The Oort Cloud may therefore be made partly of bodies born in the Sun's own disk, stored later in a much wider configuration. A reservoir like this dissolves the simple image of a solar system ending at the last planet. Neptune is deep inside the story. The Kuiper Belt is still inner architecture compared with the far Oort Cloud. Even the heliopause, crossed by Voyager, lies near compared with the distances proposed for the outer cloud. A spacecraft may enter interstellar plasma and still require centuries to approach the inner edge of the Oort Cloud, and many thousands of years more to pass through its full extent. These distances do not make the region less solar. They show that the Sun's different kinds of influence fade at different rates. The cloud's members are icy because they are thought to be remnants of the cold outer formation zones of the solar system, though their present orbits may no longer tell a simple story of birthplace. A body that formed near the giant planets could have been scattered outward by them. Another may have been affected by early stellar passages. Some fraction of material in distant reservoirs around stars may even be exchanged under certain conditions, though the details remain uncertain. The Oort Cloud is not a tidy cabinet of primordial samples. It is a long storage of bodies whose origins, transfers, and disturbances are entangled with the early solar system's dynamics. When one of these bodies is nudged inward, it may become a long-period comet. For most of its descent, it remains small and faint. Only as it enters the warmer inner regions does sunlight begin to release gas and dust, making the coma and tail visible. The comet seen from Earth is therefore the brief luminous end of a much older and colder path. Its orbit may be nearly parabolic when first observed, a sign that it has come from far away and may not return for an immense span of time, or may be altered by planetary encounters and leave the system entirely. The visible comet is a temporary expression of the hidden cloud. The isotropy of long-period comet arrivals is central to the inference. If comets came mainly from a flat disk, their inclinations would cluster near the ecliptic. Instead, many long-period comets arrive from steeply inclined and retrograde paths distributed across the sky. This does not mean every comet belongs to the Oort Cloud or that every distant orbit has a simple history. It means that the population of long-period comets, taken as a whole, points toward a source that surrounds the Sun much more broadly than the Kuiper Belt does. Above and below the planetary plane, the cloud may extend as fully as it does along the plane itself. The phrase cloud should be held gently. There is no mist, no glowing envelope, no continuous material through which a spacecraft would pass. The bodies are separated by enormous distances, and most would remain unseen even from nearby unless an instrument knew where to look. A passage through the Oort Cloud would not feel like entering a dense region. It would be a passage through vast emptiness in which, somewhere far away, small icy nuclei continued on their long solar orbits. The name is a map of probability, a way of describing where many small bodies may be distributed, not a substance filling space. Because the Oort Cloud is inferred, uncertainty belongs to it naturally. Its population size is estimated, not counted. Its inner structure is modeled, not surveyed. Its outer edge is gradual, because the Sun's gravitational hold weakens into the gravitational field of the galaxy rather than ending at a line. Some objects may be stripped away by passing stars, others may be sent inward, still others may remain for billions of years, never brightening enough to enter the catalogue of comets. The science is strong enough to make the cloud a standard part of solar system structure, but not complete enough to make it a photographed territory. The distant cloud also reframes the earlier chapters. The disk made the plane. Asteroids showed that the plane could be crossed within the planetary region. Comets showed that steep paths could link the inner system to distant reservoirs. The Kuiper Belt and scattered disk revealed icy populations beyond Neptune, still tied in various ways to the old disk and to planetary migration. Detached objects hinted at a transition toward more remote histories. The Oort Cloud gathers those threads into the largest gravitational architecture of the Sun, where the question of above and below no longer points to a thickness around a disk, but to a surrounding sphere of possibility. In this outermost gravitational province, the Sun is both central and small. It holds the orbits, yet from the distance of the cloud it would not dominate the sky as it does from Earth. The planets would be hidden near it, reduced to an inner arrangement too close to the central light to matter individually. The comet there belongs to the solar system by gravity and by origin, but it lives most of its life in a region touched by the galaxy's wider field. The solar system has not ended. It has become loose. That looseness prepares the next turn in the chronicle. If the Oort Cloud shows how far the Sun's gravity may keep small bodies, the Voyager spacecraft show how a human-made object can leave one kind of solar boundary while remaining far inside another. They do not travel through the Oort Cloud yet. They have crossed the heliopause, carrying instruments above and below the planetary sheet along real measured trajectories. After the inferred cloud, the story narrows again to two machines, their paths, their fading power, and the layered meanings of departure from the solar system. Chapter 10. Voyagers above and below the planetary sheet. After the inferred distances of the Oort Cloud, the chronicle narrows to two actual paths. Voyager 1 and Voyager 2 do not measure the far comet cloud, and they will not reach its inner regions for centuries, but they have already crossed a different kind of boundary, the boundary of the sun's outward plasma flow. Their journeys make the layered solar system concrete. A spacecraft can leave the planetary region, pass beyond the heliopause, and still remain far inside the sun's gravitational story. Departure, once again, depends on which surface or influence is being named. Both Voyagers left Earth in 1977, launched into a rare arrangement of the outer planets that allowed gravity assists to carry them from one giant world to another. The timing mattered because Jupiter, Saturn, Uranus, and Neptune were placed in a geometry that would not return for many generations. A spacecraft could borrow orbital energy from one planet and alter its path toward the next, not by violating conservation, but by exchanging an almost immeasurable fraction of momentum with a world so massive that the planet's own change became negligible. In this way, the outer solar system became not only a set of destinations, but a sequence of bends in a path. Voyager 2 launched first on August 20th, and Voyager 1 followed on September 5th. Their names therefore do not preserve launch order, but mission design. Voyager 1 was placed on a faster path to Jupiter and Saturn, with a trajectory that would later carry it away from the ecliptic toward the north side of the planetary plane. Voyager 2 followed a slower route that allowed encounters with all four giant planets, continuing from Jupiter to Saturn, then Uranus, and finally Neptune. The two spacecraft became a pair not because they moved together, but because their separate paths allowed the solar system to be sampled in different directions. At Jupiter, the Voyagers entered a system large enough to feel almost planetary in its own right. The planet's magnetosphere extended far into space. Its moons presented distinct geological histories, and Io revealed active volcanism beyond Earth. Those findings belong to planetary science more than to the question of above and below, but they mattered for the spacecraft trajectories. The Jupiter encounters adjusted the paths onward, increasing speed relative to the Sun and aiming the machines towards Saturn. The flight showed how navigation in the solar system uses gravity not as a passive background, but as part of the route itself. Saturn divided the two futures. Voyager 1's path was chosen to pass close to Titan, Saturn's largest moon, whose thick atmosphere had already made it scientifically valuable. That encounter bent Voyager 1 out of the plane of the planets, ending any possibility of continuing to Uranus and Neptune. The choice was deliberate. Titan was important enough to justify the departure from the grand planetary sequence. After Saturn, Voyager 1 moved away from the ecliptic on a northward trajectory, carrying the spacecraft out of the planetary sheet and into a long outward passage that no later planetary encounter would interrupt. Voyager 2 continued differently. After Saturn, it remained on a path that allowed Uranus in 1986 and Neptune in 1989, encounters still unique in spacecraft history. At Uranus, it observed a world tipped dramatically on its side, with moons and rings moving in a system unlike Jupiter's and Saturn's in several important ways. At Neptune, it passed the last giant planet, observed Triton, and then continued outward on a path angled south of the ecliptic. The planetary tour ended there, not because the spacecraft had reached the solar system's edge, but because the last major planet had been passed. The geometry of the two trajectories matters for this episode because they became real, measured departures above and below the planetary sheet. Voyager 1 moved north of the ecliptic after Saturn. Voyager 2 moved southward after Neptune, traveling away from the Sun at a substantial angle below the plane. These directions are not moral or absolute directions, only descriptions relative to the ecliptic reference surface established by Earth's orbit. Still, they give the question a tangible form. Above and below the solar system are not only regions where natural bodies travel, they are also directions into which human instruments have been sent. A spacecraft leaving the ecliptic does not pass into a separate domain. It continues through the heliosphere, through thinning solar wind, through magnetic structure, through populations of energetic particles, and eventually into interstellar plasma beyond the heliopause. The planets remain behind near their old plane, but the Sun's influence surrounds the departing craft in all directions. Voyager 1 and Voyager 2 therefore moved away from the disk while staying inside the Sun's larger bubble for decades. Their paths show how the solar system can be flat in its planetary architecture and spherical or asymmetric in its plasma environment at the same time. Ed Stone became the steady interpreter of this long passage. As project scientist for the Voyager mission, he helped connect data from the spacecraft to the changing scientific meaning of their location. During the planetary encounters, the mission spoke through images, magnetic measurements, charged particles, infrared observations, ultraviolet data, and radio science. Later, when cameras were turned off and the planets were far behind, the mission spoke more quietly through particle counts, magnetic fields, and plasma waves. Stone's role was to keep continuity across that transformation, so that the same spacecraft could be understood first as planetary explorers and then as boundary instruments. The transformation took patience because the outer heliosphere is too large for sudden comprehension. Voyager 1 crossed the termination shock in 2004, entering the heliosheath, where the solar wind had slowed after meeting the pressure of the surrounding interstellar medium. Voyager 2 crossed the termination shock in 2007, but at a different distance from the Sun, which helped confirm that the heliosphere was not symmetric in a simple way. These crossings were not visual events, they were changes in particle behavior, plasma conditions, and the character of the surrounding flow. The instruments marked them because the eye could not. In 2012, Voyager 1 crossed the heliopause and entered interstellar space in the plasma sense. Galactic cosmic rays increased. Particles associated with the solar wind dropped away. The magnetic field did not change in all the ways some models had expected, which made the interpretation careful rather than immediate. Plasma wave measurements later helped determine that the spacecraft was moving through denser plasma than it had encountered inside the heliosphere, supporting the conclusion that it had crossed into the local interstellar medium. A boundary had been passed, but the passage had to be read through evidence arriving piece by piece. Voyager 2 crossed the heliopause in 2018, and its crossing was especially valuable because it still carried a working plasma instrument. Voyager 1's plasma instrument had not been operating for many years, so some of its environmental information had to be inferred indirectly. Voyager 2 could measure aspects of the plasma more directly, giving scientists a second crossing in a different direction and with different instrumental strengths. The southern path mattered. It showed that the heliopause could be sampled below the planetary plane as well as above it, adding another line through a boundary that cannot be understood from one trajectory alone. The heliopause did not end the voyagers belonging to the Sun. Their velocities are sufficient for them not to return, but they remain far inside the distance range associated with the Oort Cloud. The Sun's gravity still lies behind their paths, and the long comet reservoir, if the standard picture is correct, remains far ahead. One kind of solar system has been left, the region dominated by solar wind plasma. Another kind has not, the region where bodies may still be bound or historically tied to the Sun's gravity. The spacecraft make that distinction more clearly than a diagram can. A Voyager path is thin almost beyond ordinary thought. The spacecraft itself is small, a machine of metal, wiring, instruments, insulation, and a radioisotope power source, moving through a volume so vast that its presence changes almost nothing around it. Signals from it reach Earth as faint radio transmissions collected by large antennas of the deep space network. Those signals take many hours to arrive, crossing the distance at the speed of light, carrying engineering status and scientific measurements from a machine that has no possibility of repair. The path is physical, but knowledge of it is made from timing, frequency, telemetry, and patience. Power has become one of the mission's slow limits. The radioisotope thermoelectric generators that supply electricity have declined gradually as the plutonium fuel decays and the systems age. Instruments have been turned off over time to conserve power. Heaters, subsystems, and operating modes have been managed with unusual care because every watt matters. The spacecraft are not silent yet, but they are moving toward a future in which they will no longer be able to communicate. Their trajectories will continue after that, while their measured history closes. There is a distinction here between motion and mission. The mission depends on power, instruments, antennas, receiving stations, and commands. The motion depends on inertia and gravity. Long after the last signal is received, the spacecraft will continue outward, no longer active as observatories, but still following the paths given to them by launch, planetary encounters, and the sun's gravitational field. They will not stop at the end of communication. They will become unreported bodies, traveling through the same extended solar and interstellar environment that their instruments once measured. Above and below the planetary plane, then, the voyagers show several layers at once. They show that a spacecraft can depart from the ecliptic because a moon encounter or planetary tour gives it a tilted path. They show that the heliosphere surrounds the planetary plane rather than lying in it. They show that interstellar space can begin, in the plasma sense, while the sun's far comet cloud remains ahead. They show that leaving the solar system is not a single act, but a series of crossings, each defined by a different physical relationship. Their routes also correct the feeling that the solar system's structure should become simpler with distance. Near the planets, one can name orbits, moons, rings, and belts. Farther out, the categories shift to plasma regions, particle populations, magnetic fields, neutral atoms, distant comet reservoirs, and galactic surroundings. The farther a spacecraft travels, the fewer visible landmarks it has, but the more important the invisible conditions become. A camera becomes less central. A particle detector or plasma measurement begins to say more about where the spacecraft is than an image would. The two voyages are not enough to map everything. They are two departures through a vast and changing boundary. IBEX and other missions add global context from afar, while future instruments may refine the shape of the heliosphere and the character of the nearby interstellar medium. Still, the voyagers hold a special place because they turned theory into crossing. They passed from the planetary age of exploration into the boundary age, and they did so along paths that rose away from the old disk in opposite directions. From those paths, the chronicle can widen again. A spacecraft beyond the heliopause is no longer inside the solar wind's main domain, but it is not moving through nothing. Around it lies the local interstellar medium, thin plasma, neutral atoms, dust, magnetic fields, and the larger cavity through which the sun itself is traveling. The voyagers measured the threshold. The next question is what kind of surrounding galactic neighborhood receives them? Above and below the solar system, past the sun's bubble but far inside the Milky Way, there is not emptiness, but a faint environment shaped by older stars, local clouds, and the slow passage of the sun through the local bubble. Chapter 11. The solar system inside the local bubble. Past the sun's bubble, there is not an empty outside. The heliopause marks a change in plasma, particle populations, and magnetic influence, but it does not place the solar system against a blank surrounding darkness. Voyager crossed into a medium that was already there, thin by every earthly measure and still physically real. Around the heliosphere are interstellar ions, neutral atoms, dust grains, magnetic fields, and faint traces of older stellar history. Above and below the planetary plane, beyond the reach of the solar wind's dominance, the sun moves through a galactic neighborhood that has structure of its own. The local interstellar medium is sparse enough that ordinary intuition fails almost immediately. A cubic centimeter of air near sea level contains an immense number of molecules. A cubic centimeter of interstellar space near the sun may contain roughly a fraction of a particle to a few particles, depending on the component being measured and the region being described. Yet thinness does not mean absence. A plasma can guide magnetic fields. Neutral atoms can enter the heliosphere. Dust can scatter and absorb light. The medium around the sun is not a wall, not a fog, and not a vacuum in the strict sense. It is a low-density environment through which the heliosphere travels. The Sun is currently moving through a small portion of this environment, often called the local interstellar cloud or the local fluff. The name is informal, but the object of study is serious. A warm, partially ionized cloud of gas surrounding the heliosphere, one of several nearby cloudlets inside the larger solar neighborhood. Its material presses faintly against the solar wind and helps shape the heliopause. Some of its neutral atoms, especially hydrogen and helium, can pass into the heliosphere because they do not immediately follow magnetic field lines the way charged particles do. Instruments near Earth and on spacecraft can measure those arrivals and use them to infer the flow of matter around the Sun. This changes the scale of the earlier question. Above and below the solar system, at the level of planets and belts, one finds inclined orbits, comets, and distant icy bodies. At the level of the heliosphere, one finds plasma boundaries and energetic neutral atoms. Beyond that, the answer becomes the galactic medium itself, not dense enough to feel like a place in any ordinary way, but active enough to define the conditions through which the Sun moves. The solar system is not traveling through a pure nothing. It is immersed in a weak surrounding material, and that material has a history. The largest nearby structure in that history is the local bubble. The Sun lies inside a broad, low-density cavity in the interstellar medium, a region extending for hundreds of light years and thought to have been shaped by ancient supernovae and stellar winds. These events did not leave behind a neat hollow sphere. The local bubble has an irregular form, with surrounding denser regions, nearby star-forming clouds, and complex boundaries traced by dust, gas, and young stars. Its interior is thin, hot, and comparatively evacuated, though not empty. The Sun and its heliosphere move inside this larger cavity as a small system inside a much older galactic feature. A bubble, again, is a useful word that must be softened. There is no shining membrane around the local bubble, no smooth wall through which a star passes like a bead crossing a film. Its shape is reconstructed from measurements: dust reddening, stellar distances, gas absorption lines, X-ray emission, and the three-dimensional placement of nearby clouds. The boundary is a change in density and temperature rather than a visible surface. In this way, the local bubble resembles the heliosphere in one quiet respect. Both are real structures whose edges are known through physical conditions, not through a line the eye could follow. The European Space Agency's Gaia mission deepened this kind of mapping by measuring positions, parallaxes, and motions for enormous numbers of stars. A parallax is a small apparent shift caused by Earth's motion around the Sun, and from that shift astronomers can determine distance. With enough stars measured well, the solar neighborhood becomes three-dimensional rather than merely projected across the sky. Dust maps can then be built by comparing how starlight is reddened and dimmed along different lines of sight. The result is not just a catalogue of stars, but a spatial reconstruction of the material between them. Gaia's importance here is not that it found the local bubble by itself. The structure had been studied for decades through many kinds of observation. Its importance is that precise stellar distances allow nearby gas and dust structures to be placed more securely in space. Young star-forming regions around the local bubble appear along its surface in ways that suggest the expanding aftermath of old stellar events may have helped gather material into denser clouds. The Sun, far from being isolated in a timeless emptiness, occupies a neighborhood with cavities, shells, cloudlets, and inherited motion. The space around the solar system has been shaped by stars that lived and ended long before human instruments named the result. The old events themselves must be handled by their aftermath rather than their violence. Massive stars, at the ends of their lives, returned energy and material to the surrounding medium. Over time, such events helped heat and clear regions of interstellar gas, while denser material collected along edges and interfaces. The local bubble is understood as part of this long recycling of galactic matter. Its low density is not a primordial emptiness. It is a condition made by stellar history. by gas moved, heated, displaced, cooled, and gathered again across millions of years. Inside this cavity, the local interstellar cloud is one of the smaller regions through which the Sun is passing. The cloud has its own flow relative to the Sun, and the heliosphere responds to that flow. Neutral helium entering the heliosphere has been especially valuable because it can pass relatively far inward before being ionized, allowing instruments to measure its direction and speed. Missions and instruments studying interstellar neutral atoms have found that the local flow is not merely an abstract background. It is a measurable stream of material entering the Sun's domain and revealing the conditions immediately outside it. The experience of such a medium is almost entirely intellectual, but its physical character can be approached through slowness and sparseness. A star carries its planetary system through a cavity left by older stars. Around it, a thin cloud presses lightly against the heliosphere. Individual neutral atoms cross the boundary and move inward, passing between planets whose distances are enormous compared with atomic scale and small compared with the surrounding cloud. Nothing crowds. Nothing resembles weather in the familiar sense. Yet, over long intervals, the conditions matter because the pressure outside the heliosphere helps determine the size and shape of the Sun's protective bubble. If the Sun entered a denser interstellar cloud, the heliosphere could change. Greater outside pressure might compress it, bringing the heliopause closer to the Sun. A thinner region might allow the heliosphere to expand farther outward. These changes would unfold over long timescales as the Sun moved through different parts of the local medium. The planets would not notice such transitions as a sudden crossing in the way a traveler notices a doorway, but the radiation environment and the modulation of cosmic rays could change. The heliosphere is therefore not only made by the Sun, it is also negotiated with the galaxy. Cosmic rays enter this story because they come from outside the heliosphere and are partly filtered by it. Many galactic cosmic rays are high-energy particles, mostly protons and atomic nuclei, traveling through the Milky Way after being accelerated by energetic astrophysical processes such as supernova remnants. The solar wind and magnetic field reduce and reshape their arrival in the inner solar system, with the effect varying over the solar cycle. Beyond the heliopause, the voyagers measured a different particle environment, one less modulated by the Sun's outward flow. Above and below the planetary plane, this background of incoming particles belongs not to planetary architecture, but to the galaxy's larger energetic life. Interstellar dust adds a smaller, quieter component. Tiny grains move through the local medium, and some can enter the heliosphere. Their paths are affected by gravity, radiation pressure, and electromagnetic forces, depending on their size and charge. Spacecraft have detected interstellar dust grains, adding another way to sample the material around the Sun. A dust grain crossing the solar system is not like an asteroid in orbit around the Sun. It may be a passerby from the galactic medium, entering and leaving under a balance of forces that distinguishes it from bodies formed within the solar disk. The local bubble also reminds the chronicle that the Sun is not stationary. It orbits the center of the Milky Way along with the other stars of the galactic disk, while also moving relative to nearby gas and stars. The solar apex describes the direction in which the Sun moves relative to the local standard of rest or nearby stellar population, depending on the precise definition used. Such motions mean that the heliosphere is not a still sphere inside a still cavity. It is a moving boundary carried by a moving star through a medium that has its own flows and structures. Above and below, at this scale, begin to lose their attachment to the ecliptic. The planetary plane is still real as a description of the planets, but the local bubble is not arranged around it. The local interstellar cloud does not care about Earth's orbital plane. The galactic magnetic field, local gas flows, and dust structures belong to the Milky Way's environment rather than to the old solar nebula. A direction that is high above the planets may cut through the same interstellar cloud as a direction along the plane, or it may encounter a different column of gas and dust. The reference frame must change with the question. This is the cascade from the earlier chapters in its largest local form. The disk made a plane. the small bodies complicated it. Comets and detached objects widened it. The heliosphere surrounded it. Voyager crossed the plasma boundary above and below it. Now the surrounding medium receives those paths and places the solar system inside the galaxy's nearby material. Each scale has kept something from the one before it, but none has remained confined to it. A plane is useful until a bubble matters more. A bubble is useful until the cloud around it matters more. A cloud is useful until the galaxy's disk supplies the next orientation. The local bubble is not the final surrounding structure. It is a neighborhood, not the galaxy. Beyond its cavity are other clouds, associations of young stars, dust lanes, molecular regions, and the wider disk of the Milky Way. The solar system's movement through them belongs to timescales far longer than recorded history, and the Sun's current position is only one moment in an orbit around the galactic center that takes hundreds of millions of years. The planets continue to circle near their inherited plane while the whole system travels through a larger disk tilted differently from the ecliptic. This is where the last chapter must turn. The question that began with above and below the solar system has moved from the ecliptic to the nebular disk, from asteroids to comets, from icy reservoirs to plasma boundaries, and from the heliosphere into local interstellar matter. But the Milky Way itself has a plane, and that plane is not the solar system's plane. To understand what it means to be above the Sun, below the galaxy, or tilted between the two, the chronicle has to place the ecliptic inside the galactic disk and let the final reference frame widen around all the others. Chapter 12. Above the Sun, below the galaxy. The Milky Way supplies the next plane, and it is not the plane the planets use. Earth's orbit defines the ecliptic. The old solar nebula explains why most planets remain near it, and the invariable plane gives the solar system a reference tied more closely to its total angular momentum. But the galaxy has its own broad disk of stars, gas, dust, and dark matter, and the solar system is only one moving member inside that larger arrangement. The planetary plane is tilted steeply with respect to the galactic plane, so an object that lies far above the ecliptic may not be especially above the Milky Way at all. The meaning of direction has changed again because the structure being described has changed around it. The galactic plane is defined by the flattened disk of the Milky Way. It is the region where most of the galaxy's stars, gas, and dust are concentrated. Though the galaxy also has a central bulge, spiral structure, a stellar halo, globular clusters, and a larger dark matter halo inferred from gravitational behavior, the Sun lies in the galactic disk, in the Orion Arm or Orion Spur, a smaller structure between larger spiral arms. From Earth, the Milky Way appears as a pale band across the sky because the eye is looking through the disk from inside it. That band is not the ecliptic. It is the galaxy seen edge-on from within its own material. Galactic latitude measures angular distance above or below the Milky Way's plane, just as ecliptic latitude measures angular distance above or below Earth's orbital plane. The two systems serve different needs. Ecliptic coordinates are natural for solar system objects because planets, many asteroids, and many trans-Neptunian bodies remain close to the plane inherited from the solar nebula. Galactic coordinates are natural for mapping the Milky Way because they follow the structure of the larger stellar system in which the Sun resides. Neither system is more cosmic in an absolute sense. Each becomes exact when it is matched to the question it was built to answer. This is why the phrase above the solar system can never stand alone for long. Above relative to Earth's orbit is one direction. Above relative to the invariable plane is slightly another. Above relative to the Milky Way is a larger galactic statement, with the planetary plane turned at an angle inside it. A comet far north of the ecliptic may still lie near the galactic plane as seen from the Sun. A line of sight through the Kuiper Belt may avoid the crowded Milky Way band in one coordinate system and cross a dense stellar field in another. Direction is not false, but it is conditional. The development of galactic coordinates arose from the need to treat the Milky Way as an object rather than as a decorative band of light. William Herschel tried to infer the galaxy's shape by counting stars in different directions, though dust absorption and the sun's position limited what his method could reveal. Later astronomers built more refined maps from star counts, variable stars, clusters, radio observations, and measurements of interstellar gas. Once the Milky Way became a physical system with a disk and center, it needed coordinates of its own. The plane of the galaxy became a working surface, not because it was solid, but because it organized a vast body of observations. A reference plane at this scale becomes almost transparent in its usefulness. It does not claim to be a floor beneath the stars. It does not divide the galaxy into upper and lower rooms. It allows astronomers to say where a cluster lies, where gas is concentrated, how dust dims starlight along one line of sight and not another, and how high above the disk a halo star may travel. The same discipline that made the ecliptic useful now returns at a larger scale. Choose the structure, define the plane that belongs to it, and directions begin to acquire meaning. The Sun itself is moving around the galactic center. Its orbit is not a small circuit like Earth's yearly path, but a long galactic passage taking roughly hundreds of millions of years for one revolution. During that movement, the solar system does not glide as a rigid drawing on a page. The planets remain bound to the Sun, the Kuiper Belt, and scattered populations accompany the system. The heliosphere is carried through the local interstellar medium, and the distant Oort Cloud, if the standard picture is correct, moves with the Sun while also feeling the galaxy's tidal field. The whole arrangement travels together, a small gravitational family inside a much larger disk. The solar apex gives another orientation, naming the direction of the Sun's motion relative to nearby stars or a chosen local standard. It is not the same as ecliptic north, and it is not simply galactic north. It belongs to motion rather than to a plane. This is another quiet complication of the original question. There is the direction of planetary flatness, the direction of galactic flatness, the direction the Sun is moving, and the directions from which interstellar material flows into the heliosphere. A single word like above cannot hold them all unless the reference frame has already been named. The nested planes turn through one another without conflict. The ecliptic belongs to Earth's orbit. The invariable plane belongs to the solar system's angular momentum. The galactic plane belongs to the Milky Way's disk. The local interstellar flow belongs to the gas and plasma through which the Sun is moving. Each one is real as a description, yet none becomes final. A small icy body beyond Neptune may be classified by its inclination to the ecliptic, perturbed by the planets, influenced at great distance by galactic tides, and carried with the Sun around the Milky Way. Its motion belongs to several maps at once. This layered orientation also prevents the solar system from appearing isolated. The planets are local, but their larger environment is galactic. The Oort Cloud may be stirred by passing stars and the galaxy's tide. The heliosphere is shaped by the local interstellar magnetic field and the Sun's motion through nearby gas. Cosmic rays arrive from beyond the solar neighborhood and are modulated by the solar wind. Interstellar dust grains pass through the planetary region as visitors from the medium between stars. The solar system is a coherent system, but not a sealed one. Above and below the planetary plane, then, there are no hidden rows of planets waiting symmetrically on either side. There are inclined asteroids, steep comet paths, trans-Neptunian populations, detached objects, the wide inferred reservoir of the Oort Cloud, the asymmetrical heliosphere, spacecraft trajectories, energetic particles, neutral atoms, dust, local clouds, and the larger disk of the Milky Way turned at an angle around the whole question. Some of these are bodies, some are flows, some are fields, some are coordinate systems that allow the rest to be described without confusion. The oldest mistake would be to expect the solar system to have one edge and one orientation. It has several of each. Neptune marks a planetary limit, but not a small body limit. The heliopause marks a plasma boundary, but not a gravitational one. The Oort Cloud marks a distant reservoir, but not a visible shell. The ecliptic marks a convenient plane for planetary motion, but not the Milky Way's plane. Each boundary is true within the physical relationship that defines it, and incomplete if made to answer every question. The cascade from the beginning now becomes clear without needing to be summarized as a lesson. A disk became a direction became a reference plane. The reference plane revealed departures from itself, asteroids leaning away, comets arriving steeply, icy bodies beyond Neptune thickening the old disk, detached objects preserving more distant disturbances. Around them all, the sun's wind made a bubble. Beyond the bubble, interstellar gas and dust received the outward moving spacecraft. Around that local medium, the Milky Way supplied a larger plane, and the solar system became one tilted, moving arrangement among many others in the galaxy's disk. The final meaning of above and below is therefore not that the words are useless. They are useful, but they are never alone. They ask for a plane, a center, a motion, or a structure. Once those are given, they become exact enough for navigation, observation, and discovery. Without them, they float free of the physical world. Astronomy did not discard these ordinary words. It taught them to be careful. The solar system continues in all those frames at once. Earth keeps tracing the ecliptic. Jupiter contributes heavily to the invariable plane. Pluto, Eris, Sedna, and countless smaller bodies follow paths that rise and fall through the chosen surfaces. Voyager 1 and Voyager 2 move onward along their separate departures, no longer inside the main flow of the solar wind, still far from the distant reaches associated with the Oort Cloud. The heliosphere shifts with the solar cycle, and with the surrounding medium, the sun carries everything around the galactic center, through a neighborhood shaped by older stars. No single view gathers all of this without loss. Seen from near Earth, the planets remain close to a familiar band. Seen from the side of the ecliptic, the asteroids and Kuiper Belt gain thickness, and the comets arrive from steeper darkness. Seen from outside the heliosphere, the sun becomes a star surrounded by a plasma boundary, its planets hidden close to its light. Seen in galactic coordinates, the whole solar system is a small tilted family inside the Milky Way's disk. Each view is partial, and each view is true enough for the work it has to do. From the last chosen plane, the thought can loosen. The sun remains in motion, not hurried, not still, carrying the planets, the old disk's remnants, the distant icy bodies, and the thinning traces of its wind through the local material of the galaxy. Around it, the Milky Way keeps its wider rotation. The ecliptic remains useful near home, a clean surface drawn from Earth's yearly path, while the galactic plane lies slanted beyond it, broad with stars and dust. Between them, the solar system continues as a tilted and layered thing, not flat enough to be simple, not scattered enough to be shapeless. Far from the planets, a comet may be moving slowly through the outer dark of the sun's gravity, held only lightly, altered by influences too gradual to mark in any single year. Farther inward, the heliosphere maintains its pressure against the surrounding cloud, changing as the sun changes. Nearer still, the planets circle close to the old plane, returning again and again through the geometry left by the cloud that made them. The directions used to describe all this remain quiet agreements placed over motion so that motion can be known. Above and below, north and south, inward and outward, solar and galactic, each word settles only when the frame is chosen. The bodies do not need the words, they continue along their paths, through planes, across boundaries, inside fields, among particles, under gravity, through the larger turning of the Milky Way. The maps remain behind them, accurate for a while, revised when the next scale asks for another surface, another center, another way of naming where a thing has been. And still the sun moves on, carrying its small worlds through the galaxy's thin local medium, while the planets keep close to their inherited sheet, while distant ice waits through long intervals, while the boundary of the solar wind breathes outward and inward with the star that sustains it, and while every plane drawn through the system rests there only as a patient measure of motion, useful, temporary and still. The journey is complete. Rest well.